Well, well, well. Guess who's back? Hello, everyone. Well, let's see you. I'm back. I'm back after 2 days completely absent. Mainly due to like obligations in my internship and like other stuff. Couldn't really stream that much, when you're streaming and life gets in the way. but yeah. So I'm very happy to come back and to stream again. Yeah. That's all I can say. My hair has grown like a lot for no reason. I have absolutely no idea why. Um I don't know. I've also struggled with keeping my hair organized. It's like one of those things that in life it's an invariant. Um but it's okay. I mean, today it's a great day. We're back. We are so back. so, but okay. Time to be serious. Time to be serious. Time to actually focus on the reason why we're all here. So, as you may already know, we have been coding a memory allocator from scratch, and it has been. Let's see. We started last Saturday. So we've been coding for 4 days, excluding the 2 days where I couldn't stream. Today's our fifth day. Day number 5. Imagine that. Very crazy in my opinion too. I know. And today is what I would like to call the final stretch. Hopefully. Um I think this is going to be the final stretch part 1 because tomorrow we're going to stream again, I suppose, because I have to end stream today at like 6 p.m. PST. And that is, given the current time, around what, 4 hours and a half from now. So we have a limited amount of time, and I don't think we're going to be able to finish everything in that amount of time. But we're gonna be able to get a lot of stuff done. And so yeah, it's exciting to see that the project is sort of coming to that final stretch, to that final phase where we're actually implementing the memory allocator. Um, Hopefully, and I've proposed this to myself as a goal, we can sort of have a project every week or every like 2 weeks, and that way we can learn a lot. Like one project every week would be like 52 projects by the end of an entire year. That seems rather unhealthy and impossible. So it's probably going to be more like half of that, which should still be good. 26 projects, I mean, that's a lot. But most things are not completed in only 2 weeks. Sometimes you need more. So maybe that's going to be, I don't know, 10 projects in a year. On top of that, you have to account for the fact that I'm going to be in school during the fall. That is from August onwards, which means that I won't be able to dedicate as much time to streaming as I am right now. So it's going to be probably more like 5. 5 total projects, 7 total projects, 10 total projects. If we really get the motivation and discipline, maybe 20 projects in a year, but that's perhaps too much. That's perhaps too much. Either way, I digress. I feel we're looking too far into a future that has not yet materialized itself. So that being said, I hope you enjoy today's stream. I hope you also enjoy the fact that I've been playing with OBS a little bit. So hopefully the quality is a little bit better now. Today I had to stop streaming and stream again because like my internet connection is not as fast as to support like 1080p. I think we're doing just 720p. But if ever in the future it becomes possible, which is strange because the last stream I was streaming at 1080p and it went smooth. So not sure what's going on. Either way, I hope you always appreciate like a balance in colors that I made, because when I was watching the streams back to see what could be improved, um, all of the colors on my screen looked wash. Like the Visual Studio just seemed like off. Just didn't seem right. So, all right. That being said, that being said, that being said, having said, let's go straight to the coding. Welcome to the coding scene. All right. I'm still joking. Okay. Let's see. Can we extend this camera a little bit? Yes, we can. That's awesome. Um, let's see if I get closer, closer, closer. I think that's the top. Yeah, right there. That sounds perfect. Awesome. All right. So, give me a second while I get ready. Sorry for pulling on my phone on stream. I know. I know. I know. I know. Just give me 5 seconds. Okay. Um, um, all right. Sorry about that. I'm just inserting something here that is okay. Perfect. Sorry about that. But now we can get into it. So, as we were talking before, this is sort of our, you know, beautiful memory allocator. We have like all of the VS Code files and whatnot, but this is it, right? We're going to have to implement the fundamental functions, which is, well, initializing the memory. Then we have malloc, then we have free, and then realloc. Okay? So last stream, when we sort of started writing this, we started with a little layout on how to obtain information about our blocks, which, to whoever doesn't remember, was this was the layout of our blocks, right? So we're going to store size, left children, right children, parent, and color. And you may be saying, like, Sharif, what are these fields? Like, what does left child, right child, and parent refer to? And what does color refer to? Well, it is referring to a red-black tree. We are going to lay out sort of the list of free blocks as how to put it. You know, yeah. So we're going to put this as like it's gonna be a or mimic the layout of a red-black tree. Okay. This for the list of our free blocks. That way, whenever we need to accommodate some sort of request from the user, we're able to navigate the red-black tree until we find the best fit for that user's request. Okay. Now, there are a couple of things that we sort of need to consider. And it's that even though we have best fit, it is very likely that we're going to encounter situations where the block available in memory is way longer than the amount that the user is requesting. So at the beginning of a program, for example, we may have a block of memory that's, I don't know, I'm going to say something stupid, 1 megabyte long. But the user is only requesting 12 bytes. We're not going to give the user like this gigantic block just because it's the only one we have. We're just going to partition that block and give to the user a small partition that corresponds to what they asked for, right? And so we have to take that into account. At what point is it worth it to split a block in order to satisfy a user's request? Okay? 1 megabyte versus 12 bytes, of course it's worth it. 1 kilobyte against, I don't know, 48 bytes. Of course, it's worth it. But maybe you enter a situation where you have a, I don't know, 52 byte block and you want to accommodate 48 bytes, right? In that moment, like, does it really make sense to split the block just to have like a teeny tiny piece of memory that nobody is going to need because it only has 1 byte or 4 bytes or 8 bytes or 16 bytes? At what point in time do we stop and consider, yes, this thing, we should split it so that the remaining sort of space becomes another free block? So very interesting questions, very interesting questions. We will have to resolve all of them. But for now, let's focus on the fundamentals. So given that that's the structure of our memory blocks, we decided to create these block member variables, right? Member variables in the sense that they will allow us to get data from a given block, as if this was some sort of object in object-oriented programming. So the block size extracts the size, left, right, parent. The color extracts exactly what they say they extract. Okay? I've not yet tested them, but I think it's going to be all right. Now, you may be saying, well, if you have these sort of members here, right, how about this size, right? Why is there no member variable for it? The reason is that this size is here for sort of coalescing purposes. That is, whenever a block gets freed, it checks to its left to see if there is something else that is also free, so that we can merge these two blocks together and have sort of like, instead of two free blocks that are kind of small, we combine them together and now we have one huge free block, right? So to prevent sort of fake fragmentation, fake external fragmentation. So let's see. Okay. Oh, what happened? Oh, yeah. So that's all we have. And last stream, I was intending to go further, but my mind was blocked. I honestly couldn't really think straight. And so we stopped the stream, and here we are again. So let's sort of take a look at how the landscape looks and try and decide what to do next. So here we were planning on extending the heap in the beginning, maybe creating new memory blocks, having a function that allows us to do that. We partition a memory block. We need to merge memory blocks, and by that I mean having free blocks that are like, not merged or whatever. Now manage the free and allocated ones, which would be the whole red black trees infrastructure. And we realized that, well, free in a block is just a red black tree insertion, because you just insert the block into the red black tree data structure. And then allocating a block is just removing from the red black tree structure. That is, if there's a block we want to give to the user, we simply remove it from the red black tree of free blocks. So these are pretty sort of obvious ones. I think I'm going to, let's see, I'm going to erase the things we have here, because, I'm going to explain why, right? We had the theory of sort of extending the heap on the beginning. Like, what should the size of the heap be at the start of our sort of memory allocator running, right? Is the stream laggy? Let me see. Oh, no. Okay, that's great. We need to extend the heap in the beginning, but then, thinking about this sort of off camera, trying to realize, like, what's the best choice? Well, you don't really know if the user is going to use the heap in the first place, right? So if you ever allocate some sort of unnecessary memory, then that memory is going to be gone forever, right? Forever in the sense that the user is not going to be able to access it because it's ours, and we're never going to free it because we are the actual memory allocator, right? So instead, I think we can simply just start with 0. The heap is just null. There's nothing in the heap, right? And what that would allow us to do is not only to save memory in case the user never uses the heap, but to also sort of be lazy about things. That is, we will only allocate the space whenever someone actually needs it. Okay? So that's why we get rid of this. Now, we then have the discussion about how to create new memory blocks, but I think this responds to whatever you have, right? Partition memory block, and perfect. Let's see. Oh, wait, we have a message in chat. Hello, Nico address. Fun fact, did you know the gets function is the only function to ever be removed from a C standard? Really? What? Really? Wait. Why was it removed though? Let's see. Gets function C. The gets function. Okay, let me. Why is it so dangerous and why shouldn't it be used? I imagine that's the answer to my question, but I thought it was really cool to use the gets function because it is like the scanf, wherein I could get an input with white space, but read in one of the threads that it is not good to use because according to them, it is a devil's tool for creating buffer overflows, which I don't understand. If I use the gets function, I could do this. Enter your name, Keanu Reeves. If I use scanf, I could only do this. Enter your name, Keanu. So I need to revise and replace it on my gets code with fgets. The problem is now some code are not working anymore. Are there any functions other than gets and fgets which could read the whole line and which ignores the white space? So why is it a devil's tool? Because gets does not take a length parameter. It doesn't know how large your input buffer. Okay, that makes a lot of sense. That is, if you pass in a 10-character buffer and the user enters 100 characters, well, you get the point. Okay, this makes total sense. It's good that they removed it from the standard. That is kind of crazy. Gets removed from C. C's rules of gets could not have been done better. Damn, I did not know about this. Very interesting. Okay, thank you, Nico. But yeah, thankfully we're not using it in our memory allocator because that would be a lot of problems. Not sure why we would use it, maybe to accept terminal parameters somehow, but it would definitely be catastrophic. For now, we are sort of blessed with the fact that we don't really have to deal with it, and also with the fact that we have not constructed much of the memory allocator because all of the time we have spent on working on red-black trees, which is this entire file you see right here. We coded all of this from scratch, 450 lines of code, and then this, right? So in our case, with the memory blocks, we have already access to all of the possible variables that a block could store. Now, if we are to create new memory blocks, so there comes into play this sort of scenario where you say, okay, how do I create a new block, right? Suppose, I don't know, maybe the user has allocated a given amount of blocks, and out of the blocks the user has allocated, none of them are free. But then the user asks for another piece of memory, right? 12 bytes, for example. How do we create a new block? How do we make it come into existence? And it is a bit of a interesting problem to tackle, although not very difficult. It's just that we have to make sure that we are sort of thinking straight about this. And my proposal, and it depends on what you guys want, maybe you say like, oh no, that's really bad, so we will have to check that, is suppose the user has allocated, let me actually reduce the stroke width of this. Suppose the user has allocated, say 12, right? 12 bytes. So each of these, think of them as 4-byte chunks or little blocks. So 12 bytes, and then maybe the user has like 36 bytes. So then it's gonna occupy, well, actually 36 is a little bit of a big number. Maybe this one is, I don't know, 16, right? And then it occupies 4, and so on. Now, when the user asks us For another one, say an 8-byte block, how does that come into play? My proposal is we keep track of the space at the end that's free, and we don't really give it a special role. That is, from the beginning, we consider this to be a block, right? So in this case, this would be a 20-byte long block. It's just that it's not allocated, like the user is not using this. That way, we can have this in our free list. I know it may seem like we should have a special situation for it because it's like the end, right? That's the free space that we have just never touched in our lives. But it is better if you just make it conform to the already existing structure of the red black tree for the free list. And so what we do is, if this block is ever the best fit for some sort of allocation, then we can consider, okay, is the block way larger in comparison to the request? If the answer is yes, then we can decide to split this. Maybe we can say something like, okay, the user was asking for only 4 bytes. So it may be worth it to just say, you become a 4-byte block. So that would be only one of these guys. And then you become a 16-byte block that's now free, right? So we simply sort of partition the block. What this implies is the fact that our memory will be sort of completely covered by blocks. It is sort of like an open cover in the mathematical sense, in topology of your entire memory. Like every single bit, it's going to be under one of these little guys, either a free block or an allocated block. So in that sense, we never really create blocks, right? If you really think about it, we're not creating blocks. Since a memory is at every point in time covered by blocks, the only way to bring a block into existence is, is to partition an already existing block. So the way this will work is, at the beginning, we will think of a memory as one single humongous free block, right? And then after we're done, or sort of once the first allocation comes into play. So here we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So there are 14 of them, and 14 times 4, it's going to be 56. 14 times 4, 56. So at the beginning, if this is the amount of memory we have available, we're just going to have one 56-byte long block, right? If the user asks us to allocate, say, 12 bytes, then we're going to say, okay, let's now partition this block so that we have 12 bytes, 12, and these are the ones we provide to the user. And then we have the remaining space, which 56 minus 12 would be 44, right? And so we keep playing with our memory in this way, always being covered by blocks, either blocks that are occupied or free, but always, in order to bring another block into existence, we partition an existing one. Okay, so that's going to be our contract. That is going to be what we do. Although if you have a better suggestion, don't hesitate on putting it into the chat. So we won't create new memory blocks per se. We will instead partition existing memory blocks because of a mental model of how a memory is going to work. So this create block is just not going to be, right? We simply don't need that. And the only thing we need is partition block, right? So one thing to be said is, okay, our program starts, right? When the program starts, what is the sort of state that we're going to keep track of, right? We need to keep track of our free list. So that's going to be the red black tree. We also need to keep track of, I imagine, the size of our heap, just so that we know, can we allocate this given block, right? So, or like, If we cannot, then like proceed to ask the operating system for more memory. And what else? I think that's sort of all we need to keep track of, right? The tree of free blocks, like the free blocks list, and sort of something that tells us what the size of the heap is, so that we can request more memory if a request ever exceeds it. Um, do we hold on? Do we actually need that though? Do we need a number that tells us the size of the heap? And the reason why I ask this is because we could save memory by just not having it. Now that I think about it, the advantage of having a model like this one, where everything is sort of, we can think of as our entire memory is covered by blocks, it means that you cannot suffice a request whenever you cannot find a free block, right? Because the free space at the end is also classified as a free block. So if there's no free block, it means that the free space at the end also cannot accommodate this. And then we know that we need to expand our heap. So I suppose that we don't really need to keep track of that. I guess. Like, it seems like a weird thing where we can manage the heap without knowing how big it is. Although that may come into conflict with an edge case. So the only edge case I can imagine is whenever we have sort of a cap on what our heap size must be. In that case, we do need to keep track of the size. So let's read the spec and see if we have any sort of restriction with respect to that. Let's see if we can have a PDF extension. PDF visualizer or something. VS Code PDF. Thank you. Okay. So we should be able to open the document. Perfect. So there is this sort of constraint that they impose on us. And it's the fact that, let me see. I know the text is really small, so sorry about that. I'm just trying to find whatever we need. Let's see, malloc. Yeah, so since the standard C library malloc always returns payload pointers that are aligned to 8 bytes, your malloc implementation should do likewise and always return 8 byte line pointers. But there's no mention of what it is that we need to see, we look for the word size, maybe. Oh, there's 30 matches for size. It's impossible we're gonna find it. Okay, like, because what I'm thinking right now is it's not like malloc is infinite, right? If you request too much memory, there's going to reach a point where you have consumed all the memory available to you, and malloc is just going to return -1. It's going to return some sort of error. I don't remember exactly what the interface for that is. And so that leads me to think that we need to enforce the fact that the heap will never be greater than 2 to the 32 bytes, as you can see here. Right? The heap will never be greater than or equal to 2 to the 32 bytes. Right? However, be very, very careful. Yeah, there are certain amount of, we can check in a reasonable amount of time. Okay, whatever. Right? So there is that sort of question. We actually may need to do that. I don't know. Let me know what you guys think if you have a position on this. If not, I think it's very easy to simply add the variable if we ever discover that we actually need to keep track of the size. So I'm just going to code it without keeping track of the size of the heap. And then we just add it at the end if we see it's necessary. Because for now, given our mental model, I think we're completely able to just not know the size of the heap, yet be able to be completely functional. So that is an interesting thing. Never really knew that could happen. But yeah. All right. So we have right here a code. We have m a minute, then memory s break and whatnot. These were like nonsensical things we were writing before. So in m a minute, right, the sort of intention of this function is to initialize our memory allocator, right? This is like the one shot we have at initializing the data structures we need, all of the stuff we need. Okay? And as such, we should consider deeply what it is that we need. As per data structures, well, we need the red-black tree. And apart from the red-black tree to keep track of the free blocks, what else do we need? We said the heap size we're going to ignore. All the data is going to live in the nodes. So I think, yeah, I think it's only the red-black tree that we need to store. Wow, okay. So we need to keep the red-black tree alive. That is, if we initialize it here, right? If I said like, you know, red-black tree and then put like node or something, and then call this a red-black tree and whatever, right? This is not going to outlive this function's execution. Usually in C++, we would just create a class and make this a member variable, but that's not possible. So I think what we're going to have to do is we're going to have to create multiple static variables. Sorry, it seems like I haven't gotten much sleep, so yawn a lot. I'm sorry about that. So you're gonna need static variables, and of course you're gonna need a static variable sort of for the red-black tree. Right? Of course, this is not the way it's gonna be written or whatever, but it is going to be there, right? We know that we need it. So the question is, how do we store the red-black tree? In what way are we going to represent it? So what we have here, right, to our right, we can basically draw what's happening. Our free blocks are going to be organized in this sort of tree-like way. And I'm just going to ignore the colors for now. Okay? And this guy, and then this guy. Perfect. And so what's going to happen is once we finish, or like, not really finish, right? But like, once, okay. So this is the root of the tree, right? This is the root. And so in order to store the entire red-black tree, the only thing we need to store is the root, right? Because after the root, I can just go down the tree as usual. Now, the problem is the following. Suppose that me is the program, right? Sort of our malloc program, malloc, right, program. Suppose I have a pointer to the memory address where the node that represents the root lives. So that's going to be a pointer to some block in memory, right? It's just going to be pointing at that block. Now, the problem in a red-black tree is that usually we perform operations that are related to rotations. And a rotation can very easily change the root of a tree, right? So an example of that would be that if we perform a left rotation on this node, right, left rotation, then all of these guys, let's see if I remember correctly, all of these guys would go up here, and now this would become the new children. And notice that our program is still pointing at the old root, but the root isn't this one anymore. The root is this guy. The thing is, through the rotation, we couldn't really know that there was some random guy pointing at the root. So we cannot update that pointer because the red black tree is unaware of the fact that the program is holding a pointer to that guy. And there's not really it shouldn't have a reason to know. So in order to store the red black tree, I think we're going to need to go with the solution we described sort of when we were implementing the red black tree class. And it's that we are going to have a ghost node. A node that, yes, it's there, but it serves basically no purpose, right? This is a ghost. Be scared. Ghost. So the program is going to simply hold a pointer to the ghost node. And this ghost node is going to pose as the parent of the root. Yeah. And then it is going to have the root as its child. But we're going to code it so that the root of the tree is always considered to be this guy. That way, whenever we perform a rotation, we're going to be performing a rotation on a subtree, technically speaking. Which means that once a rotation happens, since it's in a subtree, it needs to update the parent of whoever the rotation was performed on. And that will imply that we're going to update this pointer guy from the ghost node to whoever the new root is. And the program's pointer just remains static because it's always pointing at the ghost. And so that way we trick the red-black tree into updating sort of the reference or information that we need. We could just skip the step of the ghost node altogether. The problem is that that would imply that the red-black tree has to be aware of the program and of anything else that has a reference to its root or a pointer to its root, which is kind of bad. And also it would be a little bit clumsy and difficult to implement in code. With a current implementation of a red-black tree, we already have the code, and we've already noticed that this approach of the ghost to node is actually pretty profitable. Profitable in the sense that the code that you write with it is just very simple, right? Sort of bookkeeping when it comes to this guy is almost free. So that's what we're going to do, okay? So in order to store the red-black tree, let me close the design. In order to store the red-black tree, we're just going to store sort of a pointer to the ghost node, right? So this guy, it's a pointer to the ghost node. So I'm just going to call it ghost node for now. But before even talking about red-black trees in general, I think we need to first talk about how on earth are we going to represent the red-black tree? Because as you can see in the design, and yes, I know I was stupid, I closed it, but here I reopened it. There is no such thing as like a data structure that you have sort of separate, where you can simply play with this data structure and move nodes around, and then the sort of each node holds a pointer to the block in memory they're referring to. There is no such thing, right? Like right now, we don't have the model be that way. Why? Because if we can optimize our memory usage, we're going to do it. And the way we've been able to perform that is by just storing the information itself inside of the block. So what that means is you're just going to have the left-right parent living in that memory block. So you cannot really move nodes around. You just update the pointers as usual. But then that also implies that we have to think carefully about how the red-black tree is going to be represented, or how we're going to write the code for the red-black tree. Currently, we have code for the red-black tree, which is great. It's awesome. But it's going to need some modifications. Also because this was in C++, so we have like access to templates and all this stuff. We simply need to modify it. We simply need to change things around. So one thing we need to take home is this guy, the node struct, because that's exactly what everything is going to be based off of, right? So we can create a struct, the node, that stores sort of the information necessary for our blocks. And now that I am remembering, I don't think that is possible. If I remember correctly, this was a point of conflict in our previous implementation. Yeah, so what we're planning on doing is we could have a node struct that simply stores, you know, the size, right? Maybe we have a heap pointer to the left child, maybe we have a heap pointer to the right child, and so on. The problem is that, okay, I'm actually going to complete them, right? T and then parent. Then after the parent, you have collar. So then maybe we created sort of an enum collar and then collar. And the problem comes here. Remember that we have a size at the end, right? This little size guy. We're just gonna include him here, size 2. Now, the problem with having a struct is user data, right? There is a field called user data that we definitely need to store. The problem is, how wide is it? Or how long is it? Well, we don't know, right? And not only that, it varies from node to node. But structs need to have their size computed at compile time. So we enter this problem when we don't really know a value, yet we want to store it at compile time or like, you know, in a struct. And that is basically just not possible. We could allocate a huge buffer, but that means that we would be like wasting incredible amounts of memory for nodes that don't really need that much. You could argue we could have like a node for 32 bits, for 64 bits, and so on and so on and so on, sort of correlating to the fact that every single block size is like a power of 2 or something like that. Maybe we can put that as a constraint, but no, it just doesn't seem like an elegant way to solve the problem. And it would also lead to a lot of internal fragmentation if the size of every block were to be a power of 2. Although I'm not, this is to say I'm not discarding that option, but it's not what we're going to do today. So we cannot really store a node itself. We're going to have to store a heap pointer, right? And I would even argue that this guy, this sort of ghost node, we can just represent it as a void pointer, right? We just put it somewhere, probably in the stack, because it's going to be like really small. And then that ghost node is going to point to whatever we have. So what I mean by that is the following. So ghost node. And then we need to store this ghost node in the stack. So I think we can, for this one, we can create a struct called ghost node. That's just going to have all of the things we already know. So sweet, let me think. Actually, no. Let's not do that. I don't want to have an extra struct that smells bad. It doesn't seem like a good option. Instead, I think that what we can do is we can create a little buffer in our, like, in the stack. That is exactly the amount of bytes that we need to allocate for a ghost node. So how many bytes is that? Well, it's going to be, and bear with me as we go through this. It's going to be size of a u int 32t. I know, 32 bits, but you know, just to keep the code versatile. And then the size of whoever is next, which would be the left pointer. So that's the size of a heap pointer, plus the size of another heap pointer and another heap pointer. So that's going to be times 3 times 3 plus the color bit. But remember that the color bit is not going to actually occupy space, as we're going to hide it inside the least significant bits of the parent. After that, we're going to need user data. And user data is just 0 because we don't have a need to store any user data in our ghost node. And finally, sort of the size, right? You could even argue there's really no reason to store either this or this or this or this or this in our ghost node. And in fact, the only things we need are size and left. And I think you're right. So I think that what we can do is we can just simply delete these two guys. And so although it's not going to be a complete node, it's just going to be these two sort of data members, the functions don't need to know that, right? If we want to access the left child of our sort of start node, the ghost node, then we can, like, the function does not need to have the whole block. It needs to have up until the moment where the left child occurs. And so we can sort of play with the devil in that sense. And I mean playing with the devil because we are thinking of this as a node, but this isn't actually a node. It's only size and left. There's no user data, there's no size, there's absolutely nothing. But we just do it while being aware, do not mess with the ghost node. Okay? So let's see. Char, expected expression. What is going on? Oh, I think I can just simply call this like a char one, and then have this be this way. Yeah. Okay, perfect. And in fact, I think I'm willing to simply say UNAT. I know that a char is the same size of a byte, according to sort of the C++ standard, and in fact, it's what defines it. The thing is, we are building this for like 8-bit architectures, right? Like where a byte is equal to 8 bits, and I just want to make that clear that it's not platform independent or something like that. So we have this variable, right? Our ghost node. It's going to be living in the stack, and for the ghost node, which is the little guy we drew over here, this is the ghost node. We're going to have him point to the root of a red black tree. So here we need to have ghost node point to the root of our red black tree, right? So now that we have sort of clear the role of the ghost node, let's continue. So initially, we begin, right? The program has just started, and this function gets called once and only once at the beginning of a program. What do we want to initialize? And my answer is going to honestly be nothing. We don't want to initialize anything. And the reason for that is because we don't want to allocate space at all, because it's also possible that the user is never really going to use the heap. So we instead perform sort of deallocation of more stuff in the heap lazily. And what that will imply is the fact, let me also shrink that because it's like, it feels kind of useless. What was I saying? Oh yeah, we don't really need to extend the heap at the beginning. We're just going to leave it at 0. The only variable we need to initialize is the ghost node, but it's going to be initialized in the stack, and it's already here, right? The only thing that we may perhaps consider doing is, I don't think we can create an initial value for a given static variable, if I remember correctly. So if I just say something like 0, it should not. Oh, never mind. Well, so we could initialize the ghost node over here, or we could do it over here. But I think we can just do it wherever it is being declared. So let's just get rid of that. And minute does nothing, right? We simply pass from it. Not much. Okay? Now, if we move on to malloc, which is the actual thing we want to implement, we're going to enter this sort of area or like conundrum, you know? First, when we start the program, there is literally nothing. So our memory is going to look like this, right? It's going to look empty, totally empty. There's nothing here. So at the beginning, there's a couple of things we need to do. Update the ghost node to point to whatever the root is. Remember that we have the invariant that we want to think of a memory as always being covered by either allocated or free blocks. And as it stands right now, that is not being true. That's not true. So we need to make this available memory have like, you know, a little like be a huge free block or like represented as a huge free block. And then we can split it and whatnot. So I think that those are like the two things that we need to do. Ghost node, making sure that the cover property is satisfied. And that's sort of it, right? So let's talk about this first iteration of malloc. We need to insert, so we need to make, well, I guess extend the heap. This would be for sort of initial, like first call to malloc, right? Or malloc, which is the name of our allocator. We are going to want to extend the heap because it's the first time they call this. So our heap is currently 0. The first call to malloc implies extending the heap. After the heap is extended, we want to think of it as a huge free block, right? What that means is that we're going to need to include that new free node in the red-black tree. And once we have it in a red-black tree, we're going to proceed as usual. So this also implies another thing. It implies that we're going to need to update the ghost node. The ghost node. This, in fact, should be automatic. Because if we code a good red-black tree, it is going to update the ghost node so automatically. And then after that, we proceed as usual, right? So first call to malloc. It's going to allocate 12 bytes. First thing we do, we have absolutely nothing. So I'm gonna grab this guy. Oh, sorry. Yeah. Okay, I'm gonna grab this guy. And first thing that happens, we don't have anything. No heap, no nothing. There's nothing allocated. First thing we need to do, well, we're gonna need to store the user's information somewhere. So we extend the heap by a given amount. In this case, it could be by the amount the user is requesting, right? So, bam, we extend the heap. Ploof. Now, after that, this may contain just random data. So what we are going to do is to make sure that we can think of the heap as this huge free block, right? That is, we register into a free blocks list, including all of the headers and all of that stuff. So then we sort of have this huge guy that says you have a free block that's 56 bytes long. This implies including this node in the red-black tree, which means filling out sort of all of those spaces, like the left, the right, the parent, and the caller. And it will also imply updating the ghost node. So notice that now our red-black tree was empty, there was nothing, but then we inserted this first element, this huge first 56 byte block. That means that the ghost node which is the guy that's going to keep track of where the root is, needs to be updated, right? Because now there is a root. So now the ghost node should be pointing at 56. After that, we proceed as usual. Why? Because we have basically initialized everything we need, right? We have a free thing that is completely sort of like a huge free block. And so now we can just proceed as we would in the case where this is not the first call to malloc. In the case where there's already a tree existing, we simply go down the tree. We see that there's only one node. So there's only one node that can suffice that request, which is 56. We grab that block 56. We allocate whatever the user needs inside it, and then we return it. So after this point in time, we do not need to think of the first sort of malloc as a special case. We proceed as usual. So let's focus on these first steps, right? The first call to nalloc or malloc or whatever. We need to extend the heap. So something that we need to do, and like sort of intrigues me a little, is the fact that we don't really know where the heap is going to be placed, right? We don't know the starting address of the heap per se. It could just be like in a random place. So what that means is it's possible that that initial pointer to, or like memory address to where the heap is just, you know, not 8-byte aligned. But we want it to be 8-byte aligned or like size T aligned. That means that we're going to first have to figure out whether or not we need to introduce padding at the beginning of our memory. So maybe we can use mmInit for that, right? Consider introducing padding at the beginning of memory. We also need, now that I realize, not only the ghost node as one of our variables, and let me actually close this visualization so that we can see the code. We're not going to only need the ghost node. We're also going to need to know what the starting address of the heap is, right? So as a static variable, we're going to need to store sort of the starting address. And the starting address, it's not going to be a heap pointer, actually. It's just going to be a char pointer, right? It's going to tell us where the heap starts, and that's all we need to know about it. Now, the question is, how do we obtain the starting address of the heap? Is there some sort of system call that we can perform, or some sort of like, you know, something provided in the mem library? Let's see. So memInit initialize the memory system model. dinit free the storage used by the memory system. No. Then sbrk, this is what we're going to use to extend the heap. Yeah. Simple model is the sbrk function extends the heap by increment bytes and returns the start address. Ooh, the start address of who? Of the new area. In this model, the heap cannot be shrunk. Okay. Reset brk, it's going to be reset the simulated break pointer to make an empty heap. Okay, that's interesting. So I assume then that maybe we need to call this guy inside of red mem reset brk to be like, let's start from scratch, please. Oh shoot, what did I do? Okay, yeah. Mem heap low, maybe this is the one we need. Return the address of the first heap byte. Perfect. So this is exactly what we need. That means then that we don't really have the need to store this starting address variable because we already have a function that gives it to us, right? So perfect. Inside of init, we may consider introducing the padding, but once again, it's possible that we don't even need padding if the user is never going to use the heap. So that means that the introduction of padding, given that we are leaving everything to be sort of a lazy allocation, right? I'm not sure if that's a good term to put into here because it's not like lazy allocation like everywhere, but it is lazy allocation in the sense that we're not going to allocate anything until the user actually starts using the heap. So let's just baptize this as lazy initial allocation. For the lazy initial allocation, we need to introduce padding. Right? So first of all, we need to detect whether or not this is our first allocation. So that's just going to be a task for us in the future. And we're just going to rely on the fact that we know how to do that. So if this is a first allocation, we introduce padding. How do we introduce padding? Well, if you give me a certain byte address, we would need to round up to the closest multiple of whatever the alignment is. So that means that we can have we could have a static variable, although there is really no need to keep track of a variable that's never going to change its value. I think it is just better if we just make it a macro, where we simply say define sort of like the alignment by 8. And I remember this is something that was suggested in the example to do. So that's great, right? We can define the alignment. We want to align by 8 bytes, right? An 8-byte pointer, because that's what the spec mentions. And let's see. So in order to make a given, let's see here, in order to introduce padding, we would need to know after memheap low, I think that's the name, memheap low. After memheap low, which is the first byte of the heap, what is the byte that's aligned to 8? Right? So sort of like padding will take place, padding will occupy from memheap low all the way to sort of next multiple of 8 over memheap low. Right? So it's going to take all of that space. But what I mean by that is, suppose that the first address of the heap is just 0. Then in that case, we would need no padding because we're already 8-byte aligned. But if it is instead, say, 1, then we would need to introduce padding in the heap so that all of these first sort of 7 blocks are occupied, except, so all of this is going to be padding, and then a heap will sort of in our minds start here, just so that it's 8-byte aligned. Because we need to return 8-byte aligned pointers, and it just makes it easier if we start the entire heap in an 8-byte aligned address. So it means that we were going to need to calculate what address follows a given alignment. And so I think we're going to, this is something else to remember, we're going to create an align sort of thing, right? That's going to allow us to simply compute what the aligned value would be for the next sort of byte that you provide. I'm not sure. So suppose we accept x as a parameter. I'm not sure if this is the way you do it with macros because I haven't really used macros that much. But what we need to do is, with that given address, actually let me call it address, with that given address, we need to round it up to the nearest multiple of 8. And so what that would mean is that to the address, we need to add whatever the alignment is, alignment, and then subtract 1 from it. and then get rid of the last however many bits represent the alignment. So what I mean by that is this. So if you have the address, say, I'm just going to play with a single byte. Imagine that each address is a single byte. 0, 0, 0, 0, 0, 0, 0, 0, right? If you have this address, then adding 8 to it makes it so that, sorry, adding 7 to it makes it so that we have a 1 here, a 1 here, and a 1 here. And then what we want to do is we want to get rid of these last 3, so 0, 0, 0. What that does is, if you are 1 more from a multiple of 8, adding 7 will sort of kick you up to the next level, right? If you add 7 to this, you're going to end up with this, an 8-byte aligned address. So after we add 7, we're always going to go up to the next level unless we are a multiple of 8, in which case we're like 1 away from the next multiple of 8. This is just like modular arithmetic, right? And so once we add 7 to the number, we simply forget about the last 3 bits, which are the ones that represent, once again, the modulo with 8, and we just make them 0 as to make it 8-byte aligned. So once we have this number, we need to AND it with, I want the rest of things to be 1s, except for those last however many guys there are. And so I guess we have a problem, because if I change alignment to something else, because what I was thinking was we can just say the negation of whatever the last 3 bytes being 1 means, which would be 7, right? 1 plus 2, 3 plus 4, 7. The problem with that is that only applies for the 8-byte version. Sorry, 8-byte version. And so if my alignment is 2 instead, this whole thing is going to fail. This is going to align me to some some weird thing. So I think that instead we're going to have to measure the amount of bits that the alignment number has, and then compute what the mask should be at compile time, and then do that, right? But I think that is just too much work, and it seems like a little bit boring. So I'm just gonna add a to-do, fix this to be compatible with any alignment. So by this, I mean the 0x7. This needs to change if we want to support the different types of alignment. Okay, we can align a given address up to sort of the next 8-byte aligned thing. Do we need something else? And I'm willing to say no. We need nothing else. Okay, perfect. So that means that here, when we malloc for the first time, we're going to introduce padding by just simply storing into it. Let's think. So first of all, our heap is empty, there's nothing. So we need to increment or sort of expand our heap. And for that, we use the mem sbrk function, right? Simple model of the sbrk function, it extends the heap by incr bytes and returns the start address of the new array. So mem sbrk, we're just going to have it be incremented by how much. So we need to allocate whatever the size of the user is, but we also need to take into account the block metadata that we're going to need. And on top of that, we're going to need the padding at the beginning of the thing, because it's the first time right? That we allocate something. We could consider just taking a small hit and just performing this operation twice. Once for the padding, and then this one would become just the usual path where you need to expand by the block metadata and the size. Um, hmm. So, okay, let's do it this way just to simplify the thought process, and then we can do all sorts of things and modify it differently, right? And like maybe optimize in the future. But for now, let's just leave it like that. The thing is, how much padding do we need? The answer is going to be whatever aligns to the sort of like heap low. So heap mem heap low. Right? Let's see. It says expression expanded from macro line. Expression must have integral type. Oh, of course. This is just a pointer, right? And so that means, ooh, because maybe we shouldn't be using numbers. We should be just using pointers. But I am not. What do you think? I think we can just use a line this way, and then I'm just going to convert this to be a I think we have uint pointer t. Yeah. So I'll just make this a uint pointer t, and perfect. Okay, then we align it, and then yeah. So this alignment minus the mem heap load. So we're going to tell it to increase the heap by the difference between the actual beginning of the heap and the desired address we would want our sort of practical heap to start at. This would have to be a UNPTRT also. Oh no, no. UNPTRT, T, and that should be fine. Perfect. Okay. So let me actually shrink this guy. All right, we introduced the padding that we need. So I'll give you an example. Right. We have I don't know why I closed the design and immediately after I need it. Suppose that the heap starts at address say 0x1. Right. Sorry. Let me reduce the size. There you go. Starts at address 0x1. Then what this is going to do is it's going to align 0x1. It's going to take it to the next multiple of 8, which would be the 0x 8. Right. I don't know why I doubted that. Okay. 0x8. And then we go to subtract from it the original value, which was 1. And the result of that, so minus 0x1, the result of that is going to be 7. So for the heap to be 8-byte aligned, we need to introduce a padding of 7. And that makes total sense. So that's what we're going to do. We introduce the padding. It's our first time. Then after that, we need to accommodate for whatever the user's request is. So it's going to be that size. I think we're going to just stick to the rule, and we're going to allocate exactly exactly what we need, and that's the size and the block metadata. And apart from that, okay, I think we're gonna have to sort of, the block metadata, like we need to have a sort of variable or constant that tells us how much that is. I think we can simply define block metadata size, I would assume. I think that's fine. And let's see, we need to store in a block as the metadata the size, and that size of uint 32c plus the size of 3 heap pointers times 3 plus the call bit doesn't count because it's going to be hidden. The user data is not metadata, and then the size, which should be twice this. So 2 times the size, and then 3 times the heap pointers. And that gives us all the metadata we need. So now we go here and then we say, well, block metadata size plus the size of the allocation, and that will give us the size of the block, right? We could consider just simply saying block size, but I may actually do that. Let me include simply a comment here, sort of a to-do, and just says, consider changing this to block size, and then like user data size. Right, it accepts that. Although I think I won't do that because it's confusing between this, the block size that extracts the size from the block, and the block size that tells me what the size of a block would be given this amount of user data. So let's just leave it like this to make it more evident what we're doing. So yeah, we introduce padding. We then allocate space for the users block. But we need to mark that space. So what we're doing right now is precisely extending the heap. We have that already. Now we need to think of it as a huge free block, right? We need to introduce this and say, okay, this is going to be now a huge free block. I'm going to want to set a lot of the things inside the block. So I think we can introduce a new variable that allows us to sort of update a given block, update block, right? And then all we need is a heap pointer to the beginning of that block. All we need is somebody that tells us, okay, this is, well, all right, well, this is the starting address of the block I want to modify, right? And then they need to tell us what it is that they want to put in there. So we would need the new size, we would need the new size, the left, the right, the parent, the color, and then the other size, but I think we just need those. So we can just say uint32t, and then size, and then a heap pointer that points to its left child, a heap pointer that points to its right child, and a heap pointer that points to its parent. And that way we're able to tell, okay, this person wants to update this information, this is going to be a void, inside that block. And so the way we're going to do it is we're just going to update it as usual. So we're going to grab the block and the heap pointer t. This would be sort of the initial address. This would be like this guy, this arrow that you can see on the right. And we want to write to it a given amount. So, let me think. I don't feel as comfortable with this. I think what we need to do is instead sort of have the memory heap low, the beginning of the heap. We convert this to a char pointer, and then we add the block to it, because that's exactly what a heap pointer is. It's just an offset from the beginning of the heap. And then at that point in time, we can modify it and say, this is a char pointer. I simply want to dereference it, and store inside it the information I need. So I think that instead of doing that, we need to now convert this to a uint32t pointer, and then wrap all of this again, and then dereference, and then make that equal to the size. And the compiler should not complain at all. Perfect. Okay, this guys, love programming and everything, but I am not going to do this all the time. We need to change this. Like, we cannot be going around just like jollying while writing this thing. This is absolutely catastrophic. So we need to figure out a way to either write this in a better way or have like a macro for it or something that just simplifies it. I know, macro here, macro there, macro everywhere. But these are like sort of basic fundamental things, right? Like aligning an address, the alignment, the block metadata size. So I think it, if you ask me, it's like justified. So let's see if we want to update the block, blah, 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 blah. So what we're doing right now is the following. We are grabbing the pointer to the beginning of the heap. Then we are offsetting. So that's this. Then we are telling C that this is a char pointer, so that when we add stuff to it, it moves 1 byte at a time. And the question is, how many bytes? Well, block many bytes, and that's why we're adding block to it. And so since block is a heap pointer, that is an offset from the beginning of the heap, that's going to make the arrow jump around until it reaches its destination, which would be the block that whatever block is pointing at. There's so many arrows in my drawing. It is getting very confusing, but let me just erase them, right? So it is going to end up landing here, right? At the beginning address of the block that block was pointing to. Now we need to store the size, but size is a 4-byte variable. So now we tell it this pointer that you have is actually a uint32t pointer. And so now it means that we can dereference it and set it to some value, which is going to be the size. That value size being a uint32t. So that's exactly what we're doing. And I'm not sure if there's a better way. I think this is just, we're just going to do this once. So I feel there's no shame in doing it. So we can simply convert this to this, and then this one should be a chassa. Although, if any of you guys has a better approach, a better way to sort of simplify whatever this abomination is, then I'll be more than happy to adopt it. Then this would be equal to left, right? So now we cannot sort of start, or like left doesn't start at the beginning of a block. It starts from the block. Size of uint ptrt. Why have I been writing them in like this way? It's fine. I'm gonna use the convention of just like adding this guy. So size of that, and then we can set what left is. Now we copy the same code for right, but now this is gonna also include the size of the left pointer. So it's gonna be plus hptr that, and then we set it to right. And then finally, the parent is going to account for the two heap pointers that were before it, and it's going to be set to for parent. And then, and here is the thing, we also need to accept a color, right? So the parent is over here, and then we need to set the exact same address, but only its last bit to whatever the color is. So we need to AND this with, let me think. So if we want the last bit, actually not the last bit, I think it's the first bit or some crazy thing like that. Yeah, the block color, it's this guy. This is what it selects. So we need to AND this guy with, okay. Setting the color. I think of, oh my god, the amount of manipulations we're performing on a single guy is absolutely insane. So I think we can AND the parent with whatever the mask for the parent is, and then we can all the all this and or it with whatever the color is. Okay. For whomever this seems confusing, because it should be confusing. As per ZM's recommendation, ZM being like a chatter that we had on our first days of the project, we're going to store color in the last 2 bits of parent, actually in just the last bit. So what's going on is this parent pointer, suppose it was only 1 byte long, so we have 1, 2, 3, 4, 5, 6, 7, 8. Notice that every single block by the spec has to be 8 byte aligned. Remember that. That means that in an address like this, right, suppose I have like some sort of parent address that looks something like that, right? In any sort of heap pointer address to some sort of block, these last 3 bits are going to always be 0 because this needs to be an 8 byte aligned pointer. So whatever we're pointing to is 8 byte aligned. And 8 byte aligned means these last 3 things are always 0. That means that the parent pointer can be represented with only these many bits. So we have 3 bits to spare. Since color is only either red or black, we can simply use the last bit to store the color. In that way, we don't create this sort of weird situation where all of these guys are aligned. The variables themselves are 4 byte aligned, because that's the size of a heap pointer type, except for this guy, which is 1 bit. And so he's going to offset everything, and then it's going to be like a massacre. So instead, we insert the color inside the parent, we hide it in there, and then we can just live our lives happy. That's why the line that separates them, rather than a hard line, it's like a little dotted line. So that we know, yes, these are different and must be thought of as different, but they are sharing the same space. So what we're doing here is setting the color. First, we grab the parent, and then we mask it with a mask that represents what's the name? Everything once except for a 0 at the end. And then we all this with color. So if color is 0, then the least significant bit is going to say 0, but if color is 1, it's going to change to 1. Now you may be asking, well, I see that the 7 is over here, so would the most significant bit be the one that's actually affected? And the reason is no. Why no? Well, because we're playing with little endian. And in little endian, the order of stuff gets sort of shifted around, where the first bit you see is the least significant bit. So that's exactly why we're doing it this way. Yeah, and because of that, we're just able to do it. So this is great. Now we set the color, and I don't think there's anything else we need to set apart from sort of the footer size, right? And the footer size is just the same size, but at the footer. And so that means that we need to know how much to skip from here on. Yeah, this one's gonna be difficult. Let's see. So we know the size of the user data. That means that, okay, bear with me. So now what we need to update, is this last guy, like, right? This size over here, we need to update him. But remember that, like, we don't have like a very easy way to simply just skip user data. We have to use the size that we have stored here in order to travel all the way to the end and update this guy. So bear with me as we perform pointer arithmetic Squid Games. So what we're going to do is we start at the heap low. We take ourselves to wherever this block is starting. I think I'm going to pull up the image on the side just to have it as reference. Right? We start at the heap low. We go to wherever the block is pointing. Then we skip size. So size of uint 32t. Then we skip the left, right, and parent pointers. So 3 times we skip the parent pointers, right? And after we skip those 3, remember color shares the same sort of space with parent, we're going to end up at the first byte of user data. We know what the amount of bytes of user data is, and that is size. So block size for this given block, right? And you may be saying, actually, what am I doing? There's something uncomfortable here. And it's the fact that, okay, I'm allowing the user to update the size of a given block. Right? So maybe I have a block, right, that is, I don't know, 12 bytes of user data. But then they tell me, oh, update this block so that it's now 16. Question is that really possible? Well, not really, right? It's possible that we have things to our right and things to the left. And if we try to expand the size, then we're just going to be like completely incinerated. Right? That shouldn't be happening. So I think we need to remove the user's need to, or like the user possibility to specify a size. A block has a size, and the only way to increase the size is to coalesce 2 blocks, to merge 2 blocks together, or to partition a given block. Oh wait, we have a new message in the chat. Wait, yo, Neg Volsa, hello, welcome to the stream. As mentioned in the title, we're writing a memory allocator from scratch, and currently we're inhabiting the land of pointer arithmetic hell as we try to sort through the problem of updating blocks. So, yeah, we're going to use a data structure to store our 3 blocks of memory, and that's going to be a red black tree, and that involves updating some data. And currently that is not looking very pretty. So I think that we are not going to allow the user to modify the size. If you want to modify the size, you're going to have to merge this with something else and then partition. So I think it's only reasonable if we do that. Call me crazy, but then this function becomes a sort of update node, right? Basically. So update block node. So that's what we're going to think of it. So this is going to be more for the red-black tree than for anything else. And the thing is, let's see, can I ask questions or just watch and learn? Oh no, just ask questions, like just do whatever you want. If you want to ask questions about anything, about what we've been doing, about what the hell is going on. Maybe you don't know what a memory allocator is, or maybe you do know, but this design is really strange, or maybe you think the code is complete garbage and that we should change it. Propose all of that. Like this, yeah, we're just learning. I'm learning too. I have never implemented a memory allocator. That's why that's sort of the reason in the first place why we're streaming this. So yeah, we're all learning together, to be honest. So if you ever have some sort of opinion, don't so don't hesitate on like, talking about it and saying it. But yeah, so currently on like the way things are laid out, I think we're just gonna need to, instead of update block node, we're just gonna create setters for all of these guys. Like this is gonna be void and then sort of block and then set left, right? And then we're just gonna pass a block, and we're going to set this block's left pointer. So it should see each pointer of the block. So okay, so we need to, I think I'm just gonna copy whatever this is, this huge expression, this one, where we get the mem heap low, then we walk to that block, then we offset by the size, and then we set whatever's there. Block set left, we pass the block that we're talking about, and then we want to pass the value that we're gonna want left to have. So HPRT left. So that sets it. Block right is also going to have its own setter. So block set right. And then we're going to have a heap pointer to the block. So we're going to say update from this block the right pointer and make it have this value, the right value. And what it's going to be is, let's do this again. We're going to start at the beginning of the heap. We're going to jump to whatever block they pointed us to. Then from this block, we're going to skip the size section, 32T. Then we're going to skip the left pointer, which is the size of heap pointer T. And then once we have done all of that, right, we are going to, well, first this needs to be converted to a char pointer, yeah. We are going to tell it, okay, what I'm going to store inside you is a heap pointer. Sorry. Heap block is a heap pointer. And so be ready to store the information. I'm going to dereference this, the entire expression, and make this equal to whatever we want to set the value to. Right. And then the compiler should stop complaining. Let's see. Is there something wrong with this? Indirection requires pointer operand. Heap pointer T. Oh, of course, you're going to be a heap pointer T pointer. Okay, perfect. Yeah, this is a little complicated, but we're just going to have to do this once. Once we have the setters, we're going to be able to, you know, be able to use the function rather than the ugly expression. So point me to whatever block we're talking about. Tell me who the new parent is going to be. And now, from the beginning of the heap, we're going to walk until the block you pointed me to. We're going to skip the size section, which is int32 bytes long. Then we're going to skip the two heap pointers that we have, which would be left and right. And those are heap pointer t. So two of them. And then once we've reached that destination, right, I need you to have in mind that you are going to store in that location a heap pointer type pointer, and then we're going to dereference it to edit that memory location and just set it to parent. Perfect. Okay, no complaints. Finally, for the block color, and I guess it's important that we create the mask because we need to ooh, this is a good one. Okay, so the problem we're having right now is the fact that color shares the same space with its parent. So if I set the parent, the color is going to be, if I just do this, the color is going to be set to 0 because the parent is 8-byte aligned and whatnot. And so instead, I think what we're going to have to do is we're going to have to first eliminate whatever trace there is of the parent, right? By just ANDing with the 0x1. So we simply preserve the least significant bit and set the rest to 0. And now we're able to store the parent by creating an OR. And so now the caller is unaffected and the parent can live there. Awesome. So one thing I do think we're going to want is we always need to check our logic, especially when it comes to such delicate programs like a memory allocator where bugs can happen at any point in time. So we're going to assert multiple things. I guess only one of them, and that is the fact that parent is an 8-byte aligned heap pointer, right? So it would just be something like parent, and then that guy converted to, or sort of modulo 8 is just 0, right? Call to undeclared function assert. ISO-C99 later, and not so long this function later. Oh, of course. I think we need to simply include. I think the name of the library is cassert, cassert. That's in C++. Is it assert.h? Okay. Let me just make sure. So let's see. Where is assert declared in C++? Sorry, not C++. In C. In C. Sorry, guys. I'm very used to C++. This is my first time working in C. Oh, okay. Assert.h. So we did have the correct one. So assert.h. Perfect. So what we want to assert is precisely that it's an 8, or like, rather than 8, it should be alignment, truly. Let's assert that. Let's also assert this with right. Assert that right is an 8-byte aligned pointer. Assert that left is also an 8-byte aligned pointer. Left. And the size, well, we don't have a setter for the size. So this is great. Perfect. All right. So we set the parent, the color is going to be there. I think there's something we want to assert, and it's the fact that we don't modify the color by accident. That is, if we get sort of assert that this block's color, and then we pass the block, is exactly the same after we perform the change. So I think like we can simply store this in some sort of pref color And then let's just add this as assert pref color, just to have it there for the sake of assertion. And then we're just gonna store whatever the color was before. Sorry, not color, block. And then we want to, in the end, assert, call to undeclared function block color. Oh, of course. So we need to declare. Okay, this is gonna be a little bit annoying. It's fine. It's fine. Oh wait, message in chat. Let's see. Why don't you work with star and then of struct for set after your calc is starting address? Okay, so I think that might actually be the best move. The reason why previously I had discarded struct, I think doesn't apply here. I think you're right. We could do this. So the problem we had before is just the mere fact that we want us to store things like these blocks of memory as a struct that had the size, the left, the right, the parent, the color, then the user data, and then the size. So that you could just say like my struct.size, my struct.parent, and whatever. And the problem with that is we cannot do that because we don't know the size of user data. And so we are going to have sort of like the size of the struct needs to be known at compile time. But I think you point out something, that makes a lot of sense. And it's the fact that like right now to play with the metadata that's at the front, forget about size here. We only need to modify sort of these 4 guys actually. So I think we could do that. The only thing I'm scared of is if we include size into that struct, we may shoot ourselves in the foot where we try to modify the size variable, but then this size at the end does not get updated. And I think we can simply just solve that by not including size at all in the struct and just making it about left, right, and parent and color. So yeah, I feel that is a very good suggestion. I think we can just do that. Yeah. So struct, if we just simply create a sort of node metadata struct, node metadata. Why node metadata? Well, because, right, everything you need to know for a red black tree node is the left, right, parent, and color. Size you don't really need. So this is exactly the metadata that you would need for a red black tree node. Yeah, I feel that's a brilliant idea. We can just have h pointer t left, and then we simplify the entire code. Because I was genuinely starting to hate how we were just doing pointer arithmetic all the time. And yeah, thank you so much. That does make a lot of like a big difference at least. And then well, we have the parent and the color coexisting in like a single place. So it's not like we can enter like the parent, and it's not like we can enter just the color. I think we can just simply bit pack this, right? We can just bit pack. Yeah, I think that's gonna be fine. We bit pack whatever the parent is, and by how much? Well, it's gonna be just the size of whatever the heap pointer is, just -1, and the 1 bit that's left, it's gonna be given to color. Perfect. I think we have it. With this no metadata, a lot of things get simplified. I think you're right. I'm gonna get rid of this update block node function. And instead we have, okay, block size. Okay, because now there's a conflict between the setters that we have and the metadata that we want to keep track of. And I genuinely don't want to have size in there because we may just make a mistake by trying to modify the size when we shouldn't. And that is like rule number 1 of any sort of API. Never, ever trust the user, and when it comes to programming, never ever trust yourself. Can we declare a field inside a struct as const? I'm not sure. I've never really had the need to have a struct with const. Can a struct field be const? I imagine yes. It would make the most sense. I'm not sure why we would ever prohibit having a const inside a struct. And let's see. Is it a good idea? Let's see. Let's look at this. So a good idea to const qualify the fields of structures in C. No. Okay, let's first see what this person is doing. Const int a, create s, destroy s, get sa, set sa. Okay, so they're basically doing the same as us, but they're just using getters and setters instead. So let's read the response. No, using const in such a way is not a good idea. By declaring your structure fields as const, you're declaring an intention that those fields will never change the value. If you then change the value after all, you're misleading both human readers of your code and the compiler. Okay, perfect. So I think we're fine. The problem here was the fact that this person was marking their struct as const, like at least this field as const, but then adding a setter to it. So it is a little bit silly. I can see why. But I think we're free to use it, which is great. I think if we just make size constant, then all of the problems are solved. And this would just be the metadata. And rather than metadata, I think we can just call it the header, right? This would be the header of the node, which also hints at the fact that like this is not the entirety of the metadata because you still have the footer, which is over here, that stores the size. And so implicitly, we're going to know like, oh, there's a reason why we cannot modify size, and this is only the header. And if we were to call it metadata, then I'd be saying like, well, what about the guy in the footer? So I think this is the perfect name. I think we can just update this. No, block metadata size stays the same. I think we just simply call this. Okay, yeah. Let's modify things. So let's simply define header size. So the size of a header is like block, right? Block header size is we have the same thing. So we have size uint32t, and then we have 3 pointers, heap pointers, and then footer define sort of block footer size, and then we make it the size of a uint32t. So, sorry, this shouldn't have a semicolon. Then we delete this guy, and then we're gonna have an error pop up where we were using whatever it was. It's not this here. So this should instead be block header size plus the size of the user plus the footer size. And I think it's like the intention is illustrated way better this way. Okay, that's fine. Perfect. And actually, I think that deserves a little comment. So thank you, Nick. Thank you, Nick Vorza. That is a great contribution. I don't know why I was playing with all the pointer arithmetic. I think it's just the fact that like when we first thought of the struct, we determined that it wouldn't be possible because you don't know the user data at compile time. So you cannot determine the struct size at compile time, which means you cannot have a struct in the first place. And I just discarded the idea of a struct. But you're totally right. Thank you so much. Okay, we're gonna use this now. So we have the header, and I think it's only proper to define a footer, right? There's a block header and then a block footer. And then a block footer is just going to contain the size of the block, which is also supposed to be constant. This is not supposed to be a heap pointer. This is supposed to be a number. So there you go. And then constant uint32t, then size. Perfect. Ooh. Variable uint 32t is not a type name. Hello? Then what is this guy? I'm confused. Oh, I think we need a semicolon here, and then maybe that fixes everything. Yeah. Okay. Great. So we have the block footer, the block header, and now, oh my god, this is so beautiful. Now we can just get rid of all of this. Oh my god! Yay! Dude, this is awesome. This is awesome. Like, yay! Now we just have everything. Our code simplifies by miles and miles. You guys know how when we were coding the red black tree implementation, I was extremely picky about like how a code looks and how everything was looking really suspicious and fishy, and how like the beauty in your code reflects sort of a good thought process. I was starting to get really annoyed by this, but I thought it was necessary. It seems like it is not. It seems like we can have a great simplification. So thank you once again, Nick Bowser. Okay, so once we have the header and the footer, right? I think, yeah, we can allocate space for users log, yeah, whatever. It is a huge tree log, yeah. Okay, so I think actually all of these guys are the same size. So this struct should just be, okay, yeah, I don't even think we need these sort of definitions. We can simply grab the struct and use it as the thing that's going to determine the size of the header. So size of block header, and then size of footer. Size of block footer. So that way we avoid a bunch of unnecessary macros. Let's see. Identifier. Oh yeah. In C you have to call the struct before whatever. It's okay. So block header, perfect. And block footer. Oh, that's perfect. That's awesome. Okay. So now what do we have? We're supposing that we are in the first call to malloc, right? If we're calling malloc for the first time, we introduce the padding so that our practical heap is 8-byte aligned. We allocate space for the users block. So we sort of, not for the users block, but for the block that we just, right, we just allocated. So there's something really important to notice here, and it's the fact that we want every block to be 8-byte aligned, which means that to the user, like suppose, so the header is going to allow us to be 4-byte aligned. The footer is going to allow us to be 4-byte aligned, right? And so let's see, the header contains how many things? So this is a 4-byte field. This is a 4-byte field, a 4-byte field, a 4-byte field. These guys share the same space, which means that you have 1, 2, 3, and 4, and 4 times 4, 16. That is still a multiple of 8, which means that all of the metadata leaves us 8-byte aligned. The problem is the size, right? So the metadata is in total 16 bytes, right? Oh no, sorry. No, we have a problem. Oh my god, dude, the footer offsets everything. So this is 16 bytes, yes, but this is 4 bytes more, so now it's 20. So now we're not 8-byte aligned. So, okay, so we need to, what I was going to describe was the following, right? If our metadata allowed us to, or like the metadata size was 8-byte aligned, then it means that we would only need to, or we would incur in a problem if, say, size is 2, right? Because then that leaves us like 10-byte aligned. So this size offsets it. So we would have to align the size that the user gives us to the next 8-byte multiple, and then we would be completely happy. But that's not the case. That's just not the case. Because since we're not 8-byte aligned, right, the metadata is like 20 bytes, we would need to always add I assume, right? I assume just to stay like aligned, like 4 bytes to make the metadata actually aligned, and then align this in case it is not already aligned. Something like that. Something like that. Although this is definitely not. Okay, so we need to fight with alignment somehow. Okay, this is gonna be to do. Make sure this is aligned, right? Like correctly. So we have, let's see, make the footer bigger. Yes and no, I feel, because even so, if we make the footer bigger, yes, we would solve the problem by having sort of the footer aligned too. But it means that we could be consuming memory where we don't need to consume it. So if we ever have a scenario where we have all of our usual sort of variables, let me see if I can delete. Oh my god. Okay, let's take a look at this block, right? A place where we have all of our usual variables and whatnot, and the footer is just this 4 byte size. Maybe the user data, right, allows everything to actually be 8 byte aligned. And then we don't need to waste space here, adding the 4 bytes that the footer needs to also be 8 byte aligned. And so maybe it is very likely that the user data will either align us to 8 bytes or be closer to 8 bytes than we would be by adding those 4 bytes to the footer. So I think we just need to do a lot of like a bit of math to figure out how much we have to add to like the user data in order to make it an 8 byte online thing. But yeah, I think that's just all. That's all we need. Okay, guys. I think I'm going to let's do this. Let's do this. Let's take a small break. Say a 20-minute break. Okay. So we can be back in 20 minutes, and after those 20 minutes, we'll continue coding. So currently, where I am is 3:37 p.m. Let's round it up to 3:40. So let's come back at 4 p.m. PST. Okay. Yeah, and I just need to take a break, stretch, drink water, etc. And once that's done, well, we'll be back, and I hope to see you all here. Remember, 4 p.m. PST. Okay. Perfect. All right. See you guys in 20 minutes. Yoo. All right. Hello, everyone. Welcome back. I don't know if the transition is like so slow. Let me see. Oh, there you go. Fixed. Okay. Welcome back, everyone. I hope your break was nice. You know, you went, grabbed a coffee, stretched. Because we're gonna continue on the memory allocator. So let's see. Are there any updates? Maybe. Okay, the chat stays the same. Oh, wait. We have more followers now. Yo, this is perfect. Excellent. Um, Thank you, FHS, for following. But yeah, and it seems like there's another secret follower because here I see 10 followers, but there's actually 9 followers I can see the name of. So we may have an anonymous follower, which is great. Um, but guys, I mean, we hit 10 followers. Let's go. Okay. Awesome. So yeah, I mean, hopefully the break was good to everyone. And let's continue with the memory allocator. So one of the situations we were approaching was the fact that this may not actually be 8-byte aligned in total. And I was thinking about it while we were on the break, and I think we have a very simple solution so that we can optimize the usage of memory as much as we can. We can simply use the align macro that we created before so that we can simply align this to whatever the alignment is. So what we're basically doing is we're allocating the next multiple of 8 that is bigger than whatever this amount could be. So remember that this is the size of this is why is it so thick? Okay, there you go. The size of this is like 16 bytes, if I remember correctly. 16. The size of this guy is 4 bytes. And so that gives us 20. So the metadata is not 8-byte aligned. But what happens if, say, the user data is only 4 bytes, right? In that case, we don't need to make the footer bigger to sort of be 8-byte aligned. The user data just so happens to align us, right? Or what happens if the user data is 7 bytes long? Then we're still not 8-byte aligned, but we are like 1 away from being 8-byte aligned, which is better than adding 4 bytes to the size. Or like to the footer in order to make it 8-byte aligned or whatever, right? So what we can do is we can simply grab the total sum of these 3 quantities. So in this case, that would be 27, if I'm seeing this correctly. Yeah, 27. And then just align this number, right? So in this case, after we align that number, the next multiple of 8 that follows is 32, which means that now we're going to have 5 extra bytes allocated, right? We simply give the user those 5 extra bytes, right? It's like we honestly don't really care that much because we cannot really use them. And they have to go in this block because otherwise the block is not 8-byte aligned. So I think if we just separate that amount of, or like sort of reserve that amount of memory by calling align, right, on the total number, then we're just going to be fine, right? So we expand our heap by that amount of bytes. We think of it as a huge free block. So now that we have sort of created a block that is of the size that the user has asked for, and remember, this should be thought of as the first call to malloc, we need to add this block to our red-black tree of free blocks, right? Because we just expanded the heap, so now there's like free space. And when we say think of it as a huge, or like not as a huge, but like as a free block, right? Because nothing dictates that it's going to be huge. This to-do is already done. So yeah, by this we mean like adding it to the red-black tree and updating the ghost node. So basically, yeah, add it to the red-black tree. To the red-black tree. To the RB tree. Okay? What does that mean? That means that we now can import all of the functions that we wrote in previous sessions related to the red black tree. So like, if you remember correctly, the first days of these series was us just coding a red black tree from scratch, which was extremely painful given the incredibly insane amount of special cases that red black trees have, especially when it comes to deletion. So you can see that there were 6 cases in total only for deletion, and insertion I think it's like 4 or 3. So it is very funny, but all of that effort is going to pay off. So when we think of it as a free block, we need to add it to the red black tree. So we would need something like insert, right? Like insert into the red black tree, so RB tree, and then we would need to pass in whatever identifier we need to insert, which in this case would just be the head pointer, sorry, the heap pointer to our block, our new block, which in this case is just 0 because this is the first block. So now we need to think of our red black tree and how we are going to represent it in our program. Okay. So we need to fix this, yes. We are not going to have this to do, so that's great. We have all the static variables, we have the block member variables. We still have some errors here with respect to, oh wait, I think they disappeared. Oh yeah, with the introduction of the structs, it disappeared. And I think that we can simply sort of introduce all of these arbitrary things and stuff like that. We can just create another file, so rb3.h and then rb3.c, just to keep the organization, right? And what we're going to include here is going to be very much related to, let me take this to workspace 1. Perfect. It's very much related to what we already have. So we're also going to need an enum that's going to represent caller. I don't know where it is. Yeah, here you go. So enum represents caller. I think we just need to import. Oh, interesting. So mm.h already has the inclusion for whatever this is. So I guess we can simply include whatever contains the definition of uint 8. Although I am unsure. Okay, let's see. Where is uint 8 t declared? In C. Okay. So it says in. Okay, try splitting std int. Okay, so standard int. And then hash include, let's try to include that. Speedint.h. Hopefully that works. Seems like it doesn't. Maybe it's the this one is the actual one. Yeah, okay. So I've been using this one, which I'm annoyed by. I like this one better. And I was just confused like why it wasn't letting me use it before. I think it's just the fact that I hadn't imported standard int. So let me just change every single one of these to uint 8t. Oh, 7, whoa. uint 8t. And do the same for the rest. So let me expand this a little bit better. Restricted an identifier. Okay, so it's just the exact same problem. I'm just going to include the standard int definition. So I'm actually include standard int. Perfect. And so now instead of uint 32t with this slash or whatever, we're just gonna have uint 32t. Sorry, this is mostly stylistic. I know it's a little bit boring, but it's just for the sake of organization. Do we have anything else? No. So if I look for u underscore, yeah, nothing else. Perfect. So now we can go to our RB tree and live a happy life because we are going to not make this full screen, hide the files. Okay, perfect. So we have the node struct, and I think this may be something that we can just use. So there is one sort of problem that the red-black tree is like, if we think of it, oh, hi Nick Vorsa, glad you're back. Basically, the way we solved the problem with alignment is very simple. We simply added up what the size would be without worrying about alignment. And then remember that we created a macro before that allows us to find the nearest next multiple of 8 for a given number, which we called align. And so we simply add them all together and we find the next multiple of 8. And whatever the difference is guaranteed to be the smallest difference. And that difference we just gift to the user, right? If the user asked for 32 bytes and the difference, that is like the amount of padding we needed to add to be 8 byte aligned is like 5 bytes, then we just give them 37 bytes. This is completely fine with the specification of malloc, which says you will give the user at least the amount of bytes that they asked for. So yeah, that's it, and that allows us to find the most memory efficient way to align ourselves. So yeah, currently we're trying to implement the red-black tree, sort of like pass it on to here, because in previous sessions, the first days of this series was implemented this red-black tree, which was very annoying due to the amount of cases that red-black trees have for removal and for insertion, but especially removal. So yeah, right now we're just trying to port that code, and since we don't really have templates, and like our red-black tree is not intended to work like in a general setting, right? This code, yes, but in the code of the memory allocator, we're gonna need to accommodate for like special types of quirks, like the fact that we cannot move nodes around. We can only update pointers, right? So if we are to swap two blocks, we cannot really do that. We also cannot change the size. So once again, we just have to deal with pointers. And now I'm trying to think of like how we want to do this, how we want to represent the red-black tree. Because every block of memory is itself a node in the red-black tree. I wanted to create a separate file, but I don't think that is going to be very possible since this guy, the red-black tree, needs to interact directly with the memory allocator in the sense that like, you know, it's gonna interact with the header and like all of this stuff. But I think we could still keep it separate just to, you know, have it like in a different file because it's a lot of code. I don't want to contaminate like the memory allocator file with all of the red-black tree code. So I think we can simply add some sort of common header for definitions, which I actually think we can simply just import mm.h because the red-black tree will be used only by the C file, so it doesn't need to be in the header, so we avoid circular references. And yeah, it seems like that works decently well, question mark. Anyways. So in a red-black tree, we're going to have color, right? But apart from color, we like the enum for color, we're gonna have nodes. And nodes need to have certain amounts of information, and that information is a block's header. So this guy. I think it would be wise to store this struct in here, like in the H file, so that the red-black tree can use it. I'm not completely sure. Because we need, let's see, we need left, right, parent, and color. We do not need size. So that would be a little bit of a problem, but it's okay. Let's just put this here, and then we're going to determine what to do. So these are custom additions to the each file. And I'm just gonna put the block header. I think it's better if instead of writing struct and then block header all the time, we simply call this block header, sort of in the way C++ would work. I may be saying this because I'm biased. Love C++ and whatnot. So yeah, here I think this struct now breaks. Yeah, so now we need to change this for block header only. Yeah, okay, perfect. And we're going to do the same with the block footer, although the red black tree should not need the block footer. And so yeah, let's see. So we add this, and we say type def struct block footer, and then we add this. Oh, let's see, message in chat. What does it say? On stage AI viewers stream booted. All right, you're getting banned, buddy. You're getting banned. All right, he's banned. Let's go. Let's continue. Okay. So we have a block footer. Now the red black tree can be aware of what's going on. We also don't need to specify that this is struct over here because of the type def. Awesome. And now, enumeration previously declared. Let me just make this. I don't know why I have this files displayed here. There you go. Let me make this bigger. Enumeration previously declared with non-fixed on the line type. Question mark? Line 31. Oh, of course. So let me just move this over here. So, whoa, what's going on? Okay, I'm gonna put this here, the color. Although color should belong to the red black tree class, and this is something that just doesn't seem right to me. It's okay. I think we can simply like add to do, right, and like, fix this BS. Like, color should be in the red black tree file. It shouldn't be here, right? But that would create like a circular dependency. But yeah, I think we can just worry about that later. What else? These guys, these are normal. So let me just erase this pseudocode. And now we have a problem. Let's see, error while processing. Unknown type name, HPTRT. Oh, of course. We need to declare both this guy and all of these macros over there in MMH. So let me just separate between the custom and like whatever was here before, just to know what was there before and what wasn't. Perfect. I think this is more than enough. And what else? Oh yeah, this is fine. Perfect. Yay. Okay. We have a red black tree here, the H thingy. And so we're not gonna have a node struct. I think we're just gonna make the red black tree interact directly with the types of the memory allocator. So we don't need to call it. And it's just gonna be like, instead of node, it's just gonna be block header. Like block header is going to be the node in the red black tree. And so for that, we need to, let's see, can we default initialize whatever the values are? Yeah, okay, so left should be null. Do we have null pointer in C++ in C? Question mark? Oh wait, but h pointers t is not a variable of size. It's not a pointer actually. It's like a little guy. It's what's his name? It's a UN32, so it's actually a number because we're treating it just like an offset. So I think we can just make this. Okay, would making it 0 be insane? Yes. Okay, we have a problem. We have a problem. Um, the problem is this. Oh, like versus this is oh. Okay, I imagine maybe you're meaning like zero or something like that. Um, expected a semicolon. Can we just not default initialize stuff in C plus in C? Let me see. Once again, I come from C plus plus, so spare my life, guys. I'm so sorry. Can you default initialize like structs in C plus plus or like fields of structs in C plus plus? Let me expand the size of this so that you get. Oh, sorry, not in C plus plus, in C. Dude, I'm so brain dead. Let's see. No, you cannot. Okay, perfectly. Great, 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 great. So can we see if there's a way to default initialize just to know? Um. Okay, you could create a constant that you use for initialization. Okay, no, that's fine. We only need to initialize it once, so it's not like we need it very frequently. Um, we just gotta make sure that we initialize it. So perfect. We have all of this stuff. We have the node already, the block header. Now we need to create our arbitrary class. C doesn't have classes, so instead we can simply create the methods the way we've been doing. So arbitrary insert, that's going to be one of the methods. It's going to be a void because it's going to insert blocks of memory into the arbitrary red black tree. Right? Have you made the connection? And we want to insert when we want to insert a block inside our red black tree, what we need to accept is the pointer to that block, right? So they need to tell us which block they want to add to the free list. And great. Now, if we are to simply create sort of the interface of everything, just to, we also need to find something in here. So probably it's going to return a heap pointer to whatever the block is. And so we are going to find something related to some sort of size, right? They need to tell us, oh, I need this kind of size. Oh, but struct da 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 da, it equals brackets. Okay, although, okay, my problem would be this is a type def, and oh no, I see what you're saying, right? When we initialize it, then we simply create like equal to and then these brackets, right? My only problem is the following. Previously in our implementation of the red black tree, we were able to, since these were like quite literally pointers, just make it a null pointer, and that would be completely fine for us, right? The only problem is that we like since these are numbers, right? HPTRT, that heap pointer, a heap pointer, it's like a 4-byte offset, right? So, okay, we are guaranteed that the heap won't be more than 2 to the 32 bytes. That means that we can represent every single position inside the heap with only 4 bytes. The problem is like pointers are not 4 bytes long, they're 8 bytes long. So we're thinking of addresses inside the heap as just offsets from the beginning of the heap, which is why this guy is a number. But that means we cannot initialize this to some value like null pointer that is universally sort of known as like a bogus value. It just makes no sense. We also cannot initialize it to 0 because there is a block at 0. So it could be the fact that just, the left is just like 0, right? It just points to the first block, which could be completely valid or something like that. And if we make it like the max value that a uint32 could have, that is a possibility, but I feel it's kind of not what we want. This just seems very, very ugly. Because we cannot have a block starting at like the last address, right? Like the biggest possible UN32T, because that means it doesn't have metadata, right? Since like it's the literal last byte the heap could ever have, a block cannot just start there. So I think that maybe a solution where we simply, not sure how elegant this is, but if we define sort of undefined and then like, well, actually, I think undefined and then something like uint32t, uint32t, and then just define it to be sort of like the max value of a uint32t. So do we have something like that? uint32t, uint32t, uint32 max. Yeah, and then we just make this to be like undefined, sort of like null pointer. I think it's just better if we use uint32 max in the first place. So I'm not sure why I'm like, or actually, it is possible that our representation of what the heap pointer will be will stop being a 32 sort of bits number. So maybe we can just simply say, sort of define here, define null HPTR, like a null heap pointer, to simply be the max, the uint32 max. I feel this is way better, yeah. So now we can make it, this is a null heap pointer, and then this guy is a null heap pointer and so on. Of course, we cannot default initialize it, but now we have something at least. So yeah, so we're gonna implement find, and when we need to find the free block, it means that we have a size that we want to find a fit for. So I think what we're going to be passing here is going to be a uint32 size. So find a block that accommodates the size that the user is currently requesting, right? This size is not the block's sort of literal size because, right, including the metabit data or anything, it will be the size for the user data. So I think this is something that is worth remarking. Here at param and then size is size of user data to find a fit for, right? So it's the size of the user data we want to find a fit for. So if the user calls, I don't know, malloc with 12, then 12 is what you should pass to me, not 12 plus the size of the metadata. That seems fine, right? That sounds about right. We know that if we don't have a value, then we simply return a null heap pointer. And finally, we have to have remove. So for remove, we don't really need we don't return anything. And we simply need a pointer to whatever block it is that you want to remove. So this is effectively our free function. And rather than node, let's just call it block to keep the convention. And great, pretty good. Okay, we have sort of the beginnings of what we want. So arbitrary find, and then arbitrary remove. Arbitrary remove. Perfect. All right. And so how do we want to represent our arbitrary? I imagine that it's just going to be, any sort of node can count as an arbitrary because in the end it's an arbitrary. Not every subtree of a red black tree is a red black tree, but for the sake of the code, we're just going to accept any block header type of thing as a red black tree. So not only do we have to pass what block we want to insert, we also need to pass in which tree do I put it, right? So that should be a block header. So you pass me the root, right? That's going to be the root. And same here, block header. And then that's going to be the root. And same here, block header, and that just has to be the root. And actually, it's not block headers that you need to pass to me. It's the block that represents the root. So there you go. Perfect. All right. Awesome. Once we write the red black tree class, like functions and stuff, we need to test them. Because it's very easy to miss details with these red black trees. So if we can first make sort of something functional, something that we can say like, okay, when we try our red black tree, these are measurable results we can take. I think we can think about it. But in the meantime, let's just write insert. So insert, we had, I'm just gonna basically copy the code that we wrote before, because that was the whole purpose. Okay, when we need to insert into our red black tree, it means that we are creating a sort of, either we're creating a new block or we are freeing a block that already existed. I think it is better if we assume that a given block already existed. So we are assuming from the block parameter, this block already exists, right? That is like, it's an actual block and we're just inserting it. Not that they call arbitrary insert to create the block and then put it in the red black tree. No, we just do the red black tree part of that. Perfect. So I think, let's see, heap pointer current to whatever the root is. Then we create a new node, but we don't really need to create a new node. We already have what that node is, which is block. We do have to change the color of that node. So inside of block, right, I'm going to take block to be sort of like a block header, right? No suitable constructor exists. Conversion to block header. Oh yeah, because the heap pointer is not necessarily a pointer, so we need to do like mem and then heap low and then add to it the block. Yeah, and then we need to convert this to a char star and then this to be a block header pointer. And this is not looking good at all, but we can then access the member variables this way. So there is something wrong about this. Like, this is, sure, I'll give it to you, technically true. It just smells bad, right? Like, we shouldn't be doing this. We should be able to simply say something like, convert to a pointer my actual heap pointer, and then just change its value. And I think that's actually what we may end up doing. Maybe if somebody has opposition to just creating a pointer function or macro that just converts our heap pointers into pointers, or has a better solution, just don't hesitate to tell me. Because right now we're in a difficult place, to say the least. Expression must have pointed class type, but it has type show. Hello? What? I imagine that I just need to close this. Yeah, okay, that was the whole thing. And then we would need to make color be equal to red. But once again, this smells really bad. It's like really fishy. At least this part. So let's see, what can we make in order to sort of support this notion? So we could define something like what? Maybe we can just call it heap pointer and then accept some sort of x that we assume to be a heap pointer. And then what we're going to replace in there is just going to be char star of mem heap low. So the beginning of the heap, to it we add whatever x is, and that's it. And that sort of gets converted. Actually, let's call it pointer because calling it heap pointer is very confusing since heap pointers are actual offsets. And I think that's gonna be fine, right? So now code simplifies to like something like this, where we just say pointer, right, of the block. Right, so make my block a pointer and think of it as a block header, and then we can just make it red. Sounds great. Can I just eliminate these parentheses or? Yeah, no. Okay, that's fine. Perfect. So, I think that this is just fine. Let's just leave it like this. We don't need to return anything from insert, so I'm gonna skip this result. Let's see. Here, if the tree is empty, then it means that whatever we add now is going to be the root. So if root is equal to what? Oh, sorry. It seems like my iPods are about to die. It seems. Ooh, 10%. That is not good. Hey, sorry. The AirPods are like the only microphone I have, so I'm gonna have to charge them one by one. Let me see. Perfect. Okay. So if the tree is empty, that is, if the root that they give us is just a null pointer, then it means that we need to link two things together. And so, oh wait, is link an existing function in C++? Okay, because we had our own function called link inside of here. So let's implement that one. And this is going to be in the helpers section. And we want some tree modifications to take place over here. And we're going to create the link function. So the link function, what it does is it just links two nodes. If I have one node here and one node here, it makes this one the parent, this one the child, and it like updates all of the pointers necessary for this to happen. So the way link works, we would need a pointer to the node one, so block, or like the to be parent, as we have it there on the right. Then we would need another pointer, but to the to be child. And finally, we need sort of a whether or not we want this to be a left child or a right child. True if left, false if right. So if we want this to be a left child, what we want to do is, well, if your parent, right, if the pointer of the to be parent, if your parent has a left child, so it would be like this. Oh, I think it's going to be really annoying to convert everything all the time to this sort of block header. So instead, I think I'm just going to make this a block pointer, right? And then just make the conversion automatically here to a block header asterisk, then there you go, block pointer. They won't let us keep the laces in our shoes coming at us. Okay, so we have the block pointer. Yes, perfect. So now we can simply replace this with block pointer and then just pass the block, and it's way more comfortable. Since we're going to be using it so much. So here, block pointer, and then we pass through the to be parent, parent. And what we want to access from it is if you have a left child, right? So different from null HPTR, then you need to update yourself. Then let me tell you, to the parent, that your left child's parent is now gone. Right, so here, okay, it's the, this is really annoying, because it's the block pointer represented by the block pointer of the to be parent, there. Then we have, wait, is there space? There you go. So block pointer of the to be parent, and then this pointer over here, I need to make its parent equal to nothing, so a null heap pointer. Right? Let's see. Implicit truncation from unsigned int to bit field changes value from this to this. Ooh, yeah, the parent is a bit field. And so if we cut, let me think. Wait, but why is it 7? Why is it 7? Because the max would be 295, right? And then it converts it to 7 after it tries to pack it. But that doesn't make sense. Oh, it's because we specified in the bit packing the amount of bytes, but bit packing is bit packing for a reason. It needs the amount of bits. So yeah. Okay, so it's gonna be this thing. So the size of the heap pointer times whatever we believe to be sort of the amount of bits in a byte. So this guy 8 and then -1. There you go. Now that should change it from 4,000 whatever to something else, I think. Yeah, so I'm just gonna say size of humanity. Okay, perfect. Okay, I think this is fine. Let's see. Just allocate the 0 block for internal use. Yeah, that could be an alternative. But I feel like both approaches are fine, right? Both the 0 block or just having the null pointer, but I see what you mean because yeah. Okay, because we have a problem here, and it's the fact that it's not like we can like set the parent unless this modifies the least significant bit. Because okay, if our parent were to be, I don't know, right? Like 24, which is an 8 byte line pointer, then would the value, yeah, implicit truncation from int to bit field changes value from 24 to 0. So this is just like a general problem with the struct. And we need to figure out what to do um, so that this doesn't happen. Why is it being converted to 0 though? Because here what we have is this is the size of a uint 8, which is 8, times the size of a heap pointer, which is 4. So that'd be the 32 bits. And then I just forget about the last bit because that guy is going to belong to color. And I don't see why storing 24 inside it is a problem because there's plenty of space. There's 31 bits that you can use for that. So I'm not at all sure what's going on. Plus, why is it 0? Because it should be instead, it should be, let's see, because 24, 1, 2, 3, 4, 5, 6, 7, 8. 24 is simply, let's see, the one, oh, try 24U. Let's see, U, to mark it as unsigned, but I don't, yeah, we have the exact same problem. Maybe if we just change this to an actual U32, will the compiler believe us? Yeah, no, so it's like a problem with the bit field itself, but I don't see why. 1, 2, 3, 4, 5, 6, 7, 8. So 24 would be represented by 1, 2, 4, 8. So 16 as 1, and then 8 also as 1. The bit field only leaves out the last bit. So the least significant bit should be this guy. There's plenty of space over here. Like, I just don't see why it's being converted to 0. That is very odd. Did we apply the right? Yeah. So make this like a heap pointer type, maybe? No. Okay. Okay, let's Google this because it doesn't make much sense to me. Implicit truncation from int to bit field makes value 0. So what's going on? Let's see. Because I don't see how it could be 0. Like, I would accept any sort of number, like any random number, but 0 specifically just doesn't make sense to me. The constant da has 24 value bits. You're trying to initialize an unsigned 21-bit bit field identity number with a constant that exceeds its range. The compiler is kind enough to warn you of this potential mistake. Furthermore, you compile a C++, which explains why. It's not sure is an error in C. Let's see. Abstruse, giving you a taste of the abysmal complexity of C++. Yeah, but this is C++. In C. I mean, I guess the explanation doesn't change, right? But because then we have a huge problem. Why is this happening? Okay, this seems to be a little bit unrelated. He creates an enum, creates a struct, Then the number of clocks, sure. Okay, if we set trig to trig rising, which is 1, trig to trig rising, but then it starts failing here. Okay, no, but it is kind of clear why. Actually, no, it's not that clear. What is trig E? Trig E, yeah, okay. Let's see. But your data definitions are not. That's precisely the problem. Trig E is an enum, not an UN32T. Neither is the enum's underlying integer type, UN32T. Making bit fields of enums is generally a shaky proposition. The problem with it is that the underlying type, an enum, is picked by the compiler. The compiler's behavior in this regard is very rarely as fully controllable as this method would require it to be. In the case at hand, you would need a compiler flag that makes the compiler. Okay, sure. But that doesn't solve our problem. Parent is still an h pointer t, and h pointer t is by definition a UN32T. And so it's unsigned. It's unsigned. You can see it here, like UN32T, right? So it should be able to hold this. Because I agree, if this was like an int, then sure you could have the situation when, since everything is ones, it takes the 2's complement and now it's negative. But once again, like that's not what we're seeing. We're just seeing 0. Like if we saw like some random number, some nonsensical number that's like super high or a negative number, sure. But we're just seeing 0. Like what on earth could happen for 24 to become 0? Like all of the bits that are being stored suddenly become 0. And like, yeah, what is it that's bothering us? Why is this happening? Um, let's see. H pointer T24, and it's the parent. Implicit conversion from H pointer T to a bit field changes the value from 24 to 0. Okay, how about say 32, which should just be a 1 in the middle of a bunch of. Let's wait for the compiler to update. It also changed this to 0. How about null H pointer? From that huge number to 7. What? Because my. Never mind, I don't know. I was gonna say that my theory is the fact that here, right, like maybe the fact that this is little Indian, it's like changing stuff because it's not the full bytes, but that doesn't really make sense. It wouldn't give you a 7. Um, yeah, we are at midfield. Ah, yawning so much. Yeah, what's going on? Okay, this is the boring part of programming where you have absolutely no idea how to find the compiler. to 7. Okay, if I subtract 1 from this, will I get 6? Yes. So if I subtract 8, will I get -1? 7 again. What? um. Yeah, it's only grabbing the last 3 bits. Like, why? Hmm. Okay. Block pointer, block pointer. The parent is indeed an H pointer. And then we just make it equal to the H pointer. It may just be like the underlying type of the struct or like some weird thing like that. Yeah, I'm not sure. I don't know. And understanding this is fundamental because we're gonna be using this all the time. So if I go back and I change this -1 and just like make it be the size it's supposed to be, even though it's a bit field, it is the size it would usually have. So will it change the warning? Let me see. Because if not, then I may be willing to say this is just some weird compiler saying something and then... Ooh, so the fact that it's a bit field just makes it immediately wrong. Interesting. Column maybe in the most significant bit. That could be a possibility, right? But then it would mean that like out of the most significant bit, so say this guy over here, we like, because allegedly the max value, which is what no H pointer has, it's like 1 1 1 1 1 1 1 1 1 1 1 1, right? Getting rid of the most significant one would still leave you with like a bunch of ones everywhere else. So you would expect it to be converted to a number that is still big, but not like as big as 4 billion or whatever it usually stores. But it's 0. Like it's just like zeros everywhere. It's just saying like, oh yeah, this thing is gonna be converted to 0. Now it's to 15. Okay. Well, let me run now. Let's see, because the C extension in VS Code is real. Yeah, to 7. 7 is just like what? What? If it's the most significant one, 7 wouldn't be what it's converted to. If it's the least significant one, 7 would also not be the one that's converted to. And the problem I have with this is if we bit pack it so that it has the size that it's supposed to have, that is like 8 times the 32 guys, right? If we just make it what it's usually supposed to be, it says now that it will be converted to... Let me run it again because the extension is usually slow. What? Okay, previously it was saying it would convert it to 15. Now it's saying it's normal, which is exactly what it's supposed to do. Is it just that the extension was extremely slow and so I need to rerun it every time to check compiling errors? Wait, oh, I know exactly what the mistake is. So previously what I had written down was size of unat t, as to say, like, unat usually represents the amount of bits there is in a byte. And so you're just getting how many bits there are in a byte. But actually, right, size of returns the amount of bytes there are. So this was just returning 1. And 1 times the size of PTRT, which is like 4, and then -1, which was 3. So only 3 bits it was taking. And since everything was set to 1, so, right, if you only have 3 bits and you set them all to 1, that's going to be 7. And that's why I was saying it was 7. So instead of this, when I changed it to 8, now it actually picked up 8 instead of 1. And now it's the actual value. And so now it should be fine. Let's see, let's run it. yeah, yeah, it changes the value from this to like this number, right? Which is like more reasonable. Okay, now we fixed the bit field. Now let's go to the discussion that we had about just reserving 0 for local use. Which, I mean, I guess it's something we can do. But because this introduces like a new problem, which you're right, is the fact that like now the parent only gets to point to like this address. But okay, we have to be careful with something because the parent is not explicitly like this, right? Okay, yeah, we have a huge problem because the 1 bit that it is cutting is which one? The most significant or the least significant? Let's see. If I make this be 1, will the value just be 1? Yes, okay, so it's cutting the most significant bit, which means we're fine. No, which means we're in trouble. Okay, so to describe my thought process here, the problem that we're having is that parent is bit packing. Yeah. 2 to the 31, yes. But remember that we know that the parent is 8 byte aligned. So we know that like if it were to remove the least significant bit, it would be removing something that we know to be 0. So then we just, whenever we look at the parent, we make sure to interpret, like to just add the least significant bit as a 0, and then it's like back again to what its value was supposed to be, right? So it's, and this is not something special because of the null pointer or whatever. It's just the way we will have to interact with the parent. Since we are bit packing the color inside, we cannot really take the color at face value. We need to assume that the color is 0. The problem here is that if it eliminates... Wait, my AirPods ran out of battery. Let me see if the other one's a little bit more charged. There you go. Okay. Is one more charged? 75%. Oh, great. Let's go. Okay. So we were saying, if you cut from the parent, independent of what null pointer is or whatever, right? Suppose we just have a block that's like very deep into the heap. If you cut from the parent the most significant bit, then you could have something like this, right? Like a reasonable address. And then when you cut the most significant bit, you're just gonna end up with like, so you have 3-bit available in parent to do whatever. Yes. That's exactly the reason why we're hiding color there. Because if you have these 8 bits, right, like suppose the address was like a single byte, then you know that since the parent is going to point at something that's 8 byte aligned, these 3 bits are just free use because you know that they're always going to be 0. The problem is that if whenever we make this sort of assignment, instead of cutting the least significant bit and storing this inside the parent so that later we can recover by just adding that 0, if instead of doing that, it eliminates the most significant one, then we cannot know what was here, right? we know what the last three are. We don't know what the one at the front is. So it's not like we can add a zero or that we can add a one because we don't know what it was. So somehow we need to guarantee that whatever is stored in the parent is this section, not this section. So I feel we're just like juggling with a lot of stuff. Let's think about how it could be simplified maybe. Like we may just need to go back to the functions where we simply say, like block parent and then let the function take care of all of this and then sort of block set parent and then let the function take care of that, right? It is a little bit annoying. I don't want that approach because I think your idea of the struct was perfect. So if we can preserve the struct somehow, that'd be great. Because currently what we would have to do would have to be like the manipulation ourselves, where we just say like, and this with whatever the negation of like 0x1 is, and then shift it to the to the left by one, right? And so now you guarantee that that's what you store. But then doing this every single time is just gonna be impossible. Not only do we introduce like a lot of bookkeeping where you have to remember to do this all the time, but it's also very sort of difficult to understand why it's there. Let's see, align the compiler can give you that, but you may have conditional definitions of header. Align, okay, the compiler can give you that, but you may have conditional. Yeah, I feel we start to get into territory where, like, the complexity of a code is telling us that we may be making a bad decision. Like, it is not true in all cases, but whenever the code starts doing things like these, it is usually a pretty good indication that we're looking at the wrong thing. And like maybe this is not the best model to look at things. Let's think if there's maybe a different way to do things. Otherwise, I think just like going back to the functions may be the play because it is definitely more understandable. It's gonna be like way simpler, but it's just not going to have that sort of snappy touch to it where you just access the numbers like butter. Order of color versus parent and bit field. Okay, so sure. I mean, so you're just suggesting on changing the. So instead of taking color to be the least significant one, take it to be the most significant one. But then, yeah, I don't think we can do that, right? Although I may be misunderstanding what you're saying. Because if we put it as the most significant one, then we enter a problem. If you mean like changing their orders this way, I'm not sure if I'm knowledgeable enough to, but no, I don't think we could do that, right? Because in this order, right, if the compiler were to, let's see, it depends on the architecture you want it in LZ, let's significant bit. Yeah, so, let's see. Let's think, because okay, can you maybe explain further what you mean? Because I may be misunderstanding. Because to me, it just currently doesn't seem plausible to put the color in the most significant bit Um, because then we sort of ruin the entire thing, given that we can only put in the least significant ones because we know that the least significant ones will always be zero. And we only know that of the least significant ones. If you're suggesting something like changing the numbers to be big endian now, I feel that would be like such a like big change for something so small that it would be like kind of bad. Um yeah, yes, agree. What should be the least significant one? Yes, I agree. Yes, we agree on that because you only know that the last three zeros, you only know that about the last three significant bits, like the least significant bits. I agree. Uh, our only problem is that C is cutting the most significant bit when it tries to fit it inside the guy, right? This guy. Um, this definition does not guarantee that. Okay. Um, like I agree, it does not guarantee that because like that's exactly a problem we're seeing. Is there a way to solve this? Because I think I'm maybe not familiar enough with how C reorders or like puts stuff in the struct to make a comment on that or like to provide a solution to it. But I agree with you. Yes, this definition is not doing that because it's instead taking the most significant one. Try reversing the order. Okay, so if we reverse the order, will that just change it? Let's see. So now we should see the odd version, or sorry, even version of, or like something like that. Let's see. Um, the way to tell would be what does 1 equal to? 1 still equals 1. So color is not taking the least significant bit. Color is still taking the most significant one. Like, right? Because like currently, if this thing is, because 1 would just be this guy, and if we somehow manage to achieve success, we would get 1 converted to 0 because the color just took the least significant bit by removing it, and then we would be fine. But that is not what's happening right now. So I think the order just doesn't matter. C just stuffs things in that way. Although I'm not willing enough to make that judgment since I don't really know. I think we may as well just sort of try and find whether C does this or not. Let's see. When bit packing does C remove the most significant bits? Let's find some sort of stack overflow. There you go. Which end of a bit field is the most significant bit? Let's wait for it to open. There you go. Okay, I'll write a C++ application. Blah, blah, blah. So a structures use a bit field as shown in the example. Okay, so this is where the problem may arise. Which end of the field is the most significant bit? Oh, no. This is, I don't think this is what we want. We don't want to know which end. Oh, okay. An implementation may allocate an addressable storage unit. If enough space remains, insufficient space. The order of allocation of a bit fields within a unit. Is implementation defined? No, I think this is not exactly what we want. We want to. Okay, I guess I'll look at the AI overview, but no, C does not inherently remove or drop the most significant bits from the packet. Instead, the bits are shifted out of your variable storage boundaries or simply discarded by the CPU. Sure. which can unintentionally alter your data if you aren't careful. How bit shifting works, we know how that works. When bit packing using the right shift operator. C shifts the bits to the right by the specified number of places. Okay. So how could we measure this? Let me try. So let's see. One way to test this could be like, at the front of a number, we had something like 1, 0, and then 1. Right? So if C++ cuts, because it's also possible that what we have, so it's also possible that the truncation mechanism just like takes place when the value actually exceeds the thing you want. So maybe that's why it doesn't act with 1. Let's see, 0x, yeah, agree. So I think that will be the one we will need. So let's see, first nibble, okay, 2, and then 2 bytes, 3 bytes, 4 bytes. Okay, perfect. And so now, yeah, it will change it to 0. So it's getting rid of the most significant one. And if we now change the order, will it make it so that it now becomes this instead of that? Let's see, let me run this again. Run now, active file. And let's see, still to 0. So it seems like C's behavior is to just cut the most significant bit. Yeah. So, oh wait, we have a new follower, Fentrox. Yay! Thank you, Fentrox, for following. We have now 11 followers. To all of the viewers that are tuning in, we're currently working on a memory allocator. We're having some problems with the way C truncates values to fit in a bit field. Yeah, so it seems like C gets rid of the most significant bit independent of what happens in order to fit your thing inside a bit field. And we wanted to get rid of the least significant one. So we could just, once again, do what we proposed, which is just shift it and then store it. But that's just not, like, remembering to do that all the time just seems extremely annoying. It's just one of those things that I wouldn't want to have. I think just because of that, because of how complex and confusing the code becomes, we may go for the function approach, where now we try, let's see. So you're suggesting try 6000. How many zeros is that? Let's see, 6, and then 1111. So you mean this literal value of just 6 as in the last byte? Because currently this wouldn't introduce a problem. I imagine that you mean like as before. So this, and then one more. It seems like it still fits. Let's see, because 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2. So it would be like this, right? And I mean, right, this is still stored. There's no conflict with this, and there shouldn't be a conflict. Is there a specific reason why you wanted me to try that hex value? 60000. Like make it the last Oh wait, no, no, no. But the 6 would mean that it's these guys over here. So it would instead be 1 1. Yeah, yeah, yeah. My bad, my bad. Yeah. So the most significant byte, right? Like the byte, it's gonna be there at the end. It's gonna look like this. So if if C removes the most significant one, then it's gonna increase its value. And if it removes the least significant one, then the value, yeah, so it's removing the most significant one, right? So yeah. Yeah, 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 yeah. That's the conclusion that we reached, right? We were saying that like independent of what happens, C just eliminates the most significant bit, independent of whatever. And because of that, like once again, we would have to shift all the time and then reshift back. Um, and just that fact makes the code extremely confusing. Nobody's gonna know why we're shifting stuff around. I think just implementing the functions is just gonna be better for us. Um, no, you're wrong. Oh, okay, okay. What? Okay, wait, wait. Why do you mention that? Like, did I say the opposite thing? Because wait, wait, wait. Okay, okay. Let's let's see, let's see what's going on. So 4 2 1, and then the rest are, yeah. So this is 8 bits, 3 4 5 6 7 8, right? And then the rest of the bits are just gonna be like zeros everywhere, right? So the value is preserved, right? Take 30, put it in whether the 31 bit is left or right. Uh, what do you mean that whether that 31 bit is left or right? Um, because it seems like if it interprets always as a 31-bit integer, then it would be getting rid of the most significant one, no? Am I hallucinating? Wait, because as a 31-bit integer, this guy would be like exactly the same. Color in front or back. Yeah, yeah, we had reached that conclusion already, right? Like I was saying, like, oh, it doesn't matter where you put the color, independent of what happens. C always gets rid of the most significant bit. Like it just right, which I think is the same. Like I think we're agreeing that like independent of what happens, it's just gonna represent it as a 31-bit, which means that it's getting rid of like the one that's at the front, which would be the most significant one, and so like we have the problem forever, right? That it doesn't matter what happens, it's just gonna get rid of the most significant one instead of the least significant one, which is the one we wanted to get rid of. And so we're gonna need to do the shifting and stuff. I'm not sure if we're agreeing. I think we are by the description of what you're saying. Because that's sort of like the conclusion we had reached before. Yeah. So let me know if that's if we are not saying the same thing. Because if we are not, it means this has some sort of way to save it, which would be great. But as it says, yes, it takes. Yes, 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 yes. We are. Okay, perfect. So what that means is the only way we could solve this is by like shifting, then storing, and then reshifting back and remembering to do that. And as I said, that simply, like the fact that our code has that complexity is a sign that we shouldn't be working that way. So I think we're going to simply have like small functions that allow us to work with sort of the fields inside a header. That way we can just simply call like get parent, right? And the function will simply allow us to do stuff like that. Saying EB32 parent color. Yes, like we thought of that. The problem is that now when you want to access the parent, you're going to have to remember to mask it with the whole like 7 f f f f f f f f f f, right? Or like or mask it with the negation of 1, right? And then when you want to talk about the color, you're gonna need to mask it with 0x1 and then set it, and then so it becomes a nightmare. It becomes a nightmare. Like it's let's try. Okay, let's do this. Let's do this. Let's try with the functions and see how it goes. If we see that it becomes too chaotic, we pause and try to sort of find a design that seems natural and that like actually allows us to code well. Because although we could do this, like we know, right? We know that we would have to shift all the time and so on. But not only would it become a little bit annoying or like mask, it's also not ideal if somebody else wants to look at the code base. And I want to make this like a programming exercise, or like, okay, let's make like good code, relatively speaking, because good code. Don't, yeah, but they can probably do that too in the case of Bitfield. Yes, but they can probably do that too in the case of Bitfield. Yes. But we could just have like the parent color thing, right? And instead of doing the mask ourselves or whatever, we just have functions take care of it. So I think that's the way we're just gonna do it. So basically, I think the way would be we have the pointer for the parent, and we just call it some obscure thing, PC, right? And then we like PC as for parent color. But why do we want it to be obscure? Because we don't want people to use this directly, right? We instead want people to use block parent and block color, right? So by the design, like the name choice, we're just sort of forcing it upon the user to not know what that is and be forced to use block parent, block color. So for now, I think that's like a temporary fix. I think for the sake of universality or uniformity, we should have the other ones, like, block left and so on. But let's just do it with parent and color for now to see how it works. So block parent is just going to return a heap pointer, right? And it needs to accept a block. And then block color, it's just going to return a color. So enum color. And it's just going to accept the block for the pointer. Pretty good. And then we define, we actually define these functions over here, where in the block member variables. Or let me transfer this to here. Oh, sorry. To Z, X, and then I paste it here. Perfect. All right. And so what we're going to do is in the block member variables, we actually define those functions that we were talking about. So this one will return a heap pointer, and it's going to be a block parent. No, block parent. And then we have a heap pointer block. And whatever we're going to return, this is simply going to be the block pointer for this little block guy, interpreted as a block pointer, yes, which is fine. We're just gonna access its PC, and we're gonna mask it with and here we have to be very careful. We're gonna have to mask it with, we want the sort of the bits at the front, right? We want to leave out the least significant one. And so we're gonna have to mask by 0x7 FFFFFF. So let's see, 0, 7, so 1, 2, 3, 4. And that way, we can obtain the parent. Yes. Oh, sorry, this is an and. No, I mean, it should be an ampersand, yeah. And then here with the uint, for the color, we're going to return a color, enum color, and then block color, and then we need to pass to it the block, pointer t block, and then we return. Oh, let's see, message in chat. Why bitfield will not work? See, I can see any problem. You mean like why are we not using the bit field and instead are doing it this way? So like again, as I mentioned, I think, let me know if I'm wrong on this, but because no matter what, the most significant bit is always the one that gets cut, and we can sort of not stop that, right? The only way to fix it would be that whenever we want to set the parent, say here the intention is to set it to null. Whenever we want to set the parent, we would need to shift to the right once, so that now the front part of the bits, which would be like, so basically what we want to preserve, if you were to assume that the heap pointer is just 1 byte long, we want to preserve this area. This is what we have agreed on. But C++ tries to fit this, and then it just eliminates the leading one, changing the number completely. And what we could do is just like shift things to the right, right? Shift it to the right so that now when it's shifted to the right, we have it that way. And then C++ is going to get rid of this one. And so now we preserve the front bits, and now we know that when we need to replace it, we just set a 0. My only problem with that is that we would have to remember to do this every single time we interact with the parent. Not only that, we would have to remember to revert it back every single time we need to read from the parent. So every read from the parent would be bit shifting now to the left, just to know its original value. And when we need to set it, we would need to remember to bit shift to the right. And then we would need to like mask and do all of this stuff that just seems rather convoluted, or not convoluted. But although it's a simple step, you would need to remember it like in every single place of the application, which just introduces an incredible like potential for bugs, right? Because you're trusting your future self to remember that every single time, and that's just like really, you know, although it's simple, it's like ugh. So instead, I'm proposing like, okay, let's simply create functions for the block and for the parent and the caller, right? And those functions are going to do sort of exactly what you're supposed to remember. And by making the name the most obscure thing ever, you're going to remember to be like, oh, I have no idea what this is. I just access the parent through block parent, right? It's sort of like a psychological trap rather than a programming problem. So yeah. So right now we're just doing that. So block parent. That to obtain the caller, we simply need to grab the block, take its PC field, and ampersand it with 8 0 0 0 0 0 0 0. And that way we can take the caller bit. So that should be fine. And then to set the parent, that's a void, and then block and set parent. And then you need to pass me the pointer to the block. And all I'm going to do is, for the block pointer that is pointed by this block, we're going to grab the PC, and we're just going to make it equal to, let's see, equal to what? Oh, we would need the new value for the parent. I'm stupid. Parent. There you go. We'll just need the most significant bits to be whatever this is. And so we just make it equal to, okay, we first ampersand with 0x blah 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 0 0 0 0 0 0 0 0 to preserve only the color. That is, we set everything to 0 except for whatever the color has, which could be 0 or 1. And then once we have done that, we all this with the new parent value. Perfect. Sounds about right. And to set the color, I'm not going to return anything. A block set color. Shoot, wait. This, there you go. So now we have an h130 block, and then an h130, sorry, an enum color of what we want the new color to be. And the only thing we need to do is we need to go to block pointer, and then block access that member variable, and then whatever is in there, just OR it with our color, right? So let's see, if the color is 1, we will want it to be there. Or it with the HPTRT version of whatever color is. Okay, I think this is this is what we have. So same PC feed. Okay, so you mentioned that we should be doing this for the like FE for the parent instead. I would agree. The problem is, and this is why, like, this is the reason why I want to create the functions, because it's really confusing to think about the bits. This is little endian. And since it's little endian, the actual, like, least significant bit is the leftmost. So the color would be here, like, it would be in the, like, at the front, to say it like in one way. If it was big endian, it would be the other way. So just to make sure I'm not becoming crazy, let's look it up. So little endian, and I want to find a picture. I think last time we were also looking at this because we were confused. Oh, why is there no images menu? Well, let me look this up again. Let's see what happened. There you go, images. Okay. So in images, oh, whoa. There's too many. There's too many. Let's see. This image could be very helpful. So let me verify that this is indeed the way it works. Data. 12, 34, 56, 78. Okay, yeah. Big endian is like the way you would think of it. And little endian is the one that's messed up. Where the bytes change order, but the bits inside them don't. Right? So if we want to modify the least significant bit, we would need to do it, but here. Right? And even then I'm doubting, because the least significant bit in that byte would not be the leftmost, but the rightmost. So, oh my God. This is, This is oh no, this is such a hellish world. Okay, so what I'm saying is this. What I'm saying is this. Like, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Let me let's go through like the actual reasoning so that we don't get confused in the future. Then four, right? So this would be like 32 bytes. It's 32 bits, right? Full bytes. Little Indian, according to what the image is saying, which let me bring the image to this workspace. One, there you go. And data structures, let me bring it to workspace two. There you go. Okay. So what is going on is the fact that like Little Indian, if you want to like, let's take the whatever they give us as an example, the 0x 1, 2, 3, 4, 5, 6, 7, 8. This first one would represent 0x 78, 0x 56, then 0x 34, and then 0x 12, right? So let's take this one as an example. 0x 12, the way we would represent it would be so 12 in hex is not actually 12, it's a different number. It's how much? Let's see. In hex you get to 16 and then that's a 1, so 16, 17. Is it 18? I think 18. Let's see. 12, what is the 12 in hex decimal? Let's see, you said it doesn't matter your picture. Your picture, how you do the value as it is in C. Okay, yeah, it's 18. You do the value as it is in C. Like, our okay, so you're just saying like imagine that like the Indianness doesn't exist. Just like suppose that it was like, big Indian and it's going to work. I am not sure about that, but let's try it out because that might actually be the case. Let's see. If I have a variable, even 32t, the storage layout, it's not its value. What do you mean exactly by that? So what I'm interpreting from what you're saying is the like it doesn't matter how it is stored. C++ will always take the leftmost one to be the most significant one and the rightmost one to be the least significant one. Is that what you're saying? Because I'm not sure that's true, but once again, this is such a confusing topic that I'll just test. Like we'll just test because I'm pretty sure I could be very wrong. Okay, what you respond to that question? Like once again, it's like, are you saying that independent of the Indianness of the underlying architecture or whatever, the leftmost one will always be the most significant bit, and the rightmost one will always be the least significant one? So yeah, okay, let's try this out. Let's find a way to test it. Because when you perform, because the way it is stored, okay, the value is the value. It doesn't know how it gets stored unless you send them byte by byte. Yes, I agree, but like right here when we're doing the masking, we're playing with like the actual bytes. So we do care about the layout of the number in the thing. I think a way to do it could be, let's see, or maybe let's just test it because I'm very confused right now. If we do something like, right, egg 8 and 0 0, so the biggest number possible, right, which should be, let's have like a rightmost one, 80 and 0 0 0 0 0 0, right? So here, this thing is not being interpreted as storage layout, it's being interpreted as a number. That we agree with. So if I want to select, right, the least significant bit, I think we can actually go to online GDB instead because it's just better because we can execute the code faster and like easier. C. I think. Hello. Are we there? Okay. Yes. Okay. Perfect. So I'm not sure why my PC is so slow. I think it may be just the streaming. So it's just the fact. Let's see. So yeah, like least significant bit is like this would be the right way to obtain the parent, and this would be the right way to obtain the color if the color is the least significant one. Right? Because so you're mentioning the PC and then FFFFFFE to obtain the parent, right? Wait, sorry, is it okay? I see here, and then I think it's like lagging. Yes. Okay. So what I'm saying is the opposite, that you need 07 FFFFF to obtain the parent. And I want to know like which one is which, right? So let's see. If we have this UN32 and instead like yes, I agree in the final sort of like in the end goal, right? Which is the fact that like we want to like separate the parent and discard color. We're just disagreeing in the form. I'm saying that this is the way to do it. Mask it like right like this, and then you're saying that it should be F F F F F F F and then E. But our end goal, I think, is the same. Yeah. So let's see. Let me close these other tabs because my PC is going really slow for some reason. I don't know why. Also, let me know if it lags at some point in time because currently I'm seeing that the stream is laggy, but I'm not sure. Okay, let's simply include. Oh yeah, here. Hashtag include stdint.h. Perfect. And now we can take this to be a number. And so let's create a number that will just have its, let's see, maybe a 0 0 0 0 0 0 0, right? Let me increase the size of the font. There you go. Perfect. So we have this number. What I'm saying is if we printf this thing, right, and we convert it to a digit and we pass in the sort of result 1, which should be UN32T, or like, you know, of grabbing num and then using the mask that I mentioned, FF, 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 right? That should take all of these guys And so it should return 0. If it is the way that you mention it, then it should be a non-zero value, right? %b of num and 0x f e. So that would would get rid of this 0 and then preserve the rest, allegedly. So it should be a non-zero value. I'm saying that this actually no, this is not a good test. Like how do we test it? How do we know which one is which? Because what this will do is it will put a 1 in the front of the byte, which means the byte is still the same. Yes, they're opposites of each other. So if it is 0, if this one up here is 0, then it means that the way you select the most significant bits. Wait, I'm going in. Let's see. Discard color by maintenance specific, or I've typed in one finger on my phone. No, it's 0, but 80 is not LSB. Okay, so let me also think, because I'm getting so confused. Let's see. What I'm arguing is we get the most significant bits with this one. So if we get the most significant bits, then we should get a big number, right? And if we don't get the most significant bits, then we should be getting something like 0, right? And then the same vice versa. So let's run it, question mark. Okay, so the first one prints 0, the second one prints -2, 14, So I think you may be right. I think you may be right on what this is. Is that the final verdict? %d and then num. So num should be, yeah, negative something, something, something. And then let me print n lines here because you cannot see it. /n, then /n. Okay, perfect. So the number is really negative. Then when we cut this, we don't cut one at the front. Okay, yeah. So, wait, why is it rendering this way? Oh, do I have to, wait. How to print unsigned int in printf C. Yeah, %u. Yeah, okay, what I imagined. So let's do %u. No. Okay. %u and %u. Okay, yeah. Ah, shoot, what? Wait, run. Yeah, okay, so the number is originally that. It selects indeed what you're saying with your approach. So it's selecting the most significant ones. So sure, yeah. No, that makes total sense. Okay, so I was wrong. I was thinking of that like the architecture modified the way things are laid out. It seems that's not the case. So let's just do FF, FE. Okay. Okay, so if that works, then it means that we can just zero out the parent, except for the least significant bit, right? And then we OR it with the parent. Yeah, okay. Perfect. So now, thank you very much. Thank you very much, Nick, because yeah, it was definitely getting confusing, at least for me. Um, but yeah, hopefully it works now. So we return now. We AND this with for the color, then it would be like AND with 1. Only get the least significant one. And then to set the color, we grab the PC and then we OR it with whatever the color is, which should make sense, right? Perfect, perfect, perfect. Okay, I think this works now. Awesome. Let's see, in line 14, that value is set 1 on MSB. Line 14. Line 14. Oh, you mean of like the previous thing we had? Yes, it's setting one of the most significant bits. So like the way to test it was like, if mine just selects everything except for the most significant bit, then it would be 0. If it selects everything except the least significant bit, then it should be the same value. So yours was the one with the same value. Yours was the one that was correct. Because it got rid of the 0 that was least significant. And so it just stayed the same because, doesn't get rid of this. Nothing changes. Mine on the other side changed the most significant one. So it like actually, screwed everything over. So yeah. Perfect. I mean, let's see, block color. I think these are the final functions that we want to have. Great. Okay. I think it's a long journey. Okay, I think this is very it's kind of complex. Like, if that was the discussion we were having while coding these functions, I cannot imagine how it would be having to repeat that process in every single line. So I'm glad we did the functions. I imagine then that what we have to do is simply block set parent, and then we just grab the parent of whoever we want, which is this guy, right? This block, and then we just tell it to set it to null pointer. And that should be fine. Identifier block set parent is undefined, but it's declared. Oh yeah, I need to declare here. String void block set parent. You should pass me the block, and you should also pass me the parent. And a very similar thing for color, where instead I mean set the color, and then the block, instead of parent, just the color. Color. Perfect. So now the arbitrary should stop complaining. Let's see. Argument of type block header. Okay. I think we can just. Oh, that's even better. Great. So we pass the pointer. Yay! Okay, now it's easier. Perfect. Cool. You have 4 gigabytes addressing with LSB, maybe set. Doesn't hurt if a line is bigger than 2. Yeah. Okay. Perfect. All right. Okay, guys. I think, it's 6 p.m. now. I have to do all this stuff. Unfortunately, like, if I could stay, it would be great. But like, I do have to do all this stuff, to like all the compromises. This is mainly a personal project. It's not for school or something. So, I have to do other things too. Unfortunately, but I'm very thankful that everyone like was here, and especially you, Nick Vorsa. It was very fun. Thank you for guiding me through the right path, because had I continued with those bits, it would have been like a very difficult bug to find. Extremely difficult. So I'm glad it didn't happen that way. And yeah, no, this is amazing, and I hope to see you guys. I was waiting removed. Thanks for the stream. Oh yeah, I'm really sorry. I think I'm gonna stream tomorrow though. Tomorrow I don't have any compromise at any sort of hour, which means that hopefully tomorrow we can just go like full on the memory allocator and just finish all of it. Well, yeah. So it's gonna be a long stream tomorrow, probably like 10 hours or something like that. But we'll see how it goes. We'll see how it goes. And yeah, thank you. Thank you to everyone. And yeah, all right. We'll see you guys. Bye bye. And yeah, remember to follow so that you know when I turn on the stream. It's probably going to be around the same hour, although it could be a little bit earlier. So it really depends a little bit. I'll try to add it to the schedule. If I cannot, just make sure to follow so that the notification arrives, telling you like, oh, SharifSegfaults uploaded and you like is streaming right now. Yeah, that's all. That's all. Thank you very much, everyone. Hope you enjoyed, and yeah, have a great rest of your day. Bye bye. Whee!